So, good morning. I welcome you all once again to the second day of this faculty development program. Now we shall start session 3 of this faculty development program. And today's speaker is Dr. Avshish Kumar from Amity Institute for Advanced Research and Studies, Noida. Dr. Avshish Kumar has experience and expertise in the synthesis and characterizations of nanomaterials, more specifically carbon nanotubes, graphene and its derivatives, graphene-based nanocomposites, and other nanostructures such as ZNO, SNO2, BI, etc. for sensing applications. Apart from synthesis of nanomaterials, his research area also includes silicon nanowires based devices, solar cells, energy storage devices. He has excellent working experience in this field, which is more than 13 years. He has published more than 55 research papers in international journals of high repute. He has also published 2 book chapters and filed 2 patents. He has hands-on working experience on various synthesis and characterizations equipments such as LPCVD, PECVD, RF sputtering, spin coating, HRTEM, FSM, Raman spectrophotometer, and XRD. He has life membership of many academic and research societies such as Indian Science Congress Association, Electron Microscopy Society of India, Semiconductor Society of India, Indian Physics Association, the Indian Physical Society, and Society for Nanoscience and Technology. Dr. Kumar has also been serving as an editorial board member and reviewer for some scientific journals. Currently, he is guiding 4 PhD students and 2 PG students. With this, I request Dr. Kumar to start his lecture. Sir, please. Yeah,
So
PPT is visible.
visible?
You can go full screen mode.
So it is in slideshow mode?
Please make it full screen.
Is it okay, sir?
No, still
Not? Just a second.
PPT is here, but it's not in full screen mode.
Okay. I'm again resharing it.
Yeah, that's my work.
Now it okay, sir?
Yeah, you go full screen mode.
I think
So
actually
make
at
it
my
in
side
presentation mode. Presentation mode.
at my side I can see it in full screen mode, but I don't know why it is not there in full screen mode. I'm just again share.
You just scroll down. Let's see whether it's visible. Yeah, it's visible, but not in presentation mode, full screen.
It's still not visible, sir, in full screen mode. Because I at my side I have just make it in full screen.
So
but I can see it in full.
can you close it and again reopen and then share?
Yes, sir. Yes. Yes, sir. Yes, sir. Just a second. Here it will not work, no? Okay. Is it okay, sir, now? Is it shared? Hello?
Sharing is okay. So please go to full screen mode. You can do it from the bottom panel or from the above slideshow is there. So you can go from there also.
Please.
So is my cursor visible?
Next. Yeah, cursor is visible. Now it is on insert. So you move it to slideshow.
Out the sound.
You move your cursor to the slideshow in the upper panel.
Okay. And
It's near this animation. Slideshow is there.
okay.
Yeah.
Setup slideshow.
Uh,
Custom slideshow. Is it okay, sir?
You can
Now?
press F5 also.
Sir, I am
No.
actually
it's not.
I'm taking classes. Just a second, sir. Maybe I can try it. At my screen, I can see it in full screen mode, but I don't know why it is not reflecting there.
Here, your screen is visible, but not in full screen mode.
Okay.
Slideshow.
Sir, near that zoom, there is a 4 icons are there. The fourth icon you press, sir.
Yeah, at the bottom,
Like
panel,
notes.
at the bottom panel, there is an
Then
icon.
next to the notes and comments. Next to the notes and comments, there are 4 signs are there. The fourth sign you press, please.
Yes, whole sign I'm pressing, and at my side I can see it in full screen mode, but I don't know why it's not reflecting there. I'm doing it. It is right now. I can see my PPT in full screen mode.
But I think it's visible, so you can continue.
I think you can continue, sir, because you can see it is visible and it's
Yeah.
visible.
Okay.
It is visible, so you continue, please.
Okay. Okay. Okay, sir. Okay. Thank you, sir. Thank you. So, a very good morning to all of you. And first of all, I would like to thank the organizers, particularly Syed Asad Hussain sir, and he gave me a chance to present the work here, what I am doing. So, it is really very nice to be the part of this FDP program. So, thank you very much, sir. So, I am basically and very nice. Thank you very much, sir, for the nice introduction which you have.
So, 1
given.
minute, sir. So, the left
Yeah.
corner, there is one from beginning. You just press that, that's enough. You can start the presentation. There is one from beginning, there is one icon there. Just press it and you can start. It will be fine.
From beginning.
The left side, top left corner, there you can see that from beginning there is one
Yes.
button.
Can you see
there.
my cursor? My cursor is visible.
No, in the
My cursor is
leftmost, in the leftmost, yes. From beginning you just
Yes.
press it.
Yes, I am pressing it, and I can see
okay,
my
sir.
PPT in full screen mode. I don't know why it is
Oh,
not
okay, sir.
reflecting there. Well, usually, I am taking the classes in online mode here in the university. I have just taken the class in, so I know that how we can make it in full screen mode. But I don't know what is the case there, because it is not showing there in full screen mode. But I can see my PPT in full screen mode. Okay, that's I think we should continue, because already 10 minutes are over now. So yes, so I am basically working on these 1D and 2D materials. Particularly, I am working on carbon nanotubes, graphene-based composites, CNT-based composites. I have already worked on there are so many papers I have published on field emission display devices, and we are also working on that sensing applications of both carbon nanotubes and graphene and its graphene-based derivatives. So, first of all, I would just like to introduce a brief about my department here in the Amity University. We are basically Amity Institute for Advanced Research and Studies and Materials and Devices. Our department is basically fully dedicated for the research, Although we have another department, Amity Institute for Renewable and Alternate Energy. In that department, we have BTech and MTech program in solar and alternate energy. So these two departments are combined here. So basically, this Amity Institute for Advanced Research, AIARS, we call it in short. So this department is basically for the research. So our main theme of our department or our institute is basically from materials to devices, then product, and then commercialization. Our director here of this department is Dr. V.K. Jain sir. So he has very good formula, 3P he called that: product, patent, and publication. So he always said that first go for the product, then patent it, and then go for the publication. So we are working in that direction. And we have very good infrastructure here in our department. Although in the university there are so many departments with they are working on various in different fields. You will so see that biotech department, then exclusively applied science department is there. So our basically main purpose is to investigate the new materials or smart materials, then develop the new and low cost technologies, product development, then technology transfer to file the paper and publish the papers in the reference. These are the areas of research over different groups. Basically, our department is interdisciplinary department. So we have the faculties from different field. Some faculties they are from bio background. Some faculties they are from chemistry background. I am basically a physicist. So I have worked on these nanomaterials a lot. So currently I am working on these graphene and its derivatives, then some metals and metal oxide based nanomaterials, silicon wires on silicon chips. We are synthesizing silicon wires on silicon chip here, making composites and using these composites for the sensing applications, for energy storage applications. We are also working here on the phase change materials based energy storage systems. I am also working, as I told you, on the field emission display devices. So, and I am also working on biosensors also. So, but these bio-nanotechnology group, there is separate group there in our department. They are working. One of group they are working on organic LEDs and solar cells. Some group, one group is working on water purification base. So there are so many these are some facilities which we have. Although I could not. I have not put it all the facilities, but this is our materials characterization laboratory here. This is the clean room facility we have here. Thin film laboratory we have here. Biochemistry lab we have. That SEM we have here. Then DLS, flame us, and UV visible spectrophotometer. FTIR we also have. I could not put that slide here. So that's about that our department. So outline of my lecture is basically, first we will discuss about the graphene and what are the properties, what can be the synthesis methods of graphene, what can be the applications, and synthesis of graphene and its derivative. I will discuss. Very recently we have optimized some parameters. So we are also working on graphene oxides, reduced graphene oxide, and graphene nanoribbons. We have synthesized here graphene nanoribbons, and we are using it for some supercapacitor applications, also for some sensing applications. Then we will discuss about 2 or 3 characterization techniques. I will discuss because there are a lot of characterization techniques: SEM, TEM, XRD, Raman, SPM, scanning power microscope, UV. So depending upon that, what properties you are looking for.
Dr. Avshish,
Yes,
I
sir.
think your PPT is not moving. So,
sir, I am on
is
outline.
it still
slide.
we are in the first? We are
Okay.
still in the first page.
Still in the first page. Oh, I don't know why so. Because
Yes.
I am on the fifth slide right now.
But still we see this type. Now it's moving. Now it's moving.
It's moving, sir?
Yes. You try again.
Yes, sir. Yes. Now this is outline slide. This is why carbon
This is theme of our department. Now I see theme of your department.
Okay. Theme of our department. So no, I'm moving ahead. Just a second. I don't.
No, still
Now
we are in
areas of
theme.
research.
You can click on the side, yeah, sidebar, yeah,
Okay.
sidebar.
I
Then
don't see.
it will work.
Find it.
Now, yeah.
Okay, sir. So yes,
Now I
actually,
see
I have
that.
already. Yes, I have already spoken about these 2 or 3 slides. I have discussed the theme of our department. So should I repeat these slides or should I move further?
I think you can move further.
Yes. I think this is the area of research we are working at. I told you different.
Yes.
So some people they are from bio background, some from chemistry background, and from physics background. Some yes, we have a separate electronic division here. We have 2 or 3 faculties in that in our department. That is a division in our department means further. So we have 2-3 people. So they usually do that all the electronics or the device which we require. So they do all the electronics of that device. So I am basically working on that synthesis part and that development of sensor part, and I'm working on that PCM based and HOS systems also. So that's all about me. I already discussed. So these are the sub facilities which we have here in the department. Some I could not list it here. I could not list here, but yes, some facilities. These are the, this is materials characterization laboratory. This is clean room facility. This is thin film laboratory. This is biochemistry lab. Here SEM we have here in the department. Even in front of me, I can see whether this SEM here. So this is DLS, FLAM, UV visible, FTIR. So many instruments we have here in our department. Even in the university, these some instruments as XRD is also there, and that cyclic voltammetry, all other type of instruments are also available in other departments. But these are the facilities which we have in our department here. So this is the outline of my talk. That first I will discuss about that introduction part, introduction about that graphene and what are the properties, applications, and what can be the synthesis techniques of. So I will discuss about the synthesis of graphene and its derivatives. Particularly, we will discuss about graphene oxide, reduced graphene oxide, and then graphene nanoribbons. I was talking about that we have also synthesized here the graphene nanoribbons, which is basically a quasi one-dimensional structure. I will just discuss a little bit about that because we are working on the graphene nanoribbons also, then characterization techniques. So some techniques I will just discuss as SEM and TEM, Raman, XRD. So then applications of graphene nanoribbons, there are its derivative or its composite based nanostructures, but particularly I will discuss about the sensing application part. So I think maybe you all are aware about that if that carbon which has so many allotropes, and if I can just differentiate between these carbon allotropes, so I can I'm just differentiating it with that based on that zero-dimensional, one-dimensional, two-dimensional, and three-dimensional. So if I talk about this zero-dimensional nanostructures of this carbon allotrope, so this is basically the nano diamond, graphene dots, carbon quantum dots, fullerenes, onion-like carbon. So these are basically the zero-dimensional structures where all the other 3 dimensions, means all the 3 dimensions, they are confined. So we call it that zero-dimensional structure. If I talk about that one-dimensional structure, so carbon nanotubes, basically we have that single wall and multi-wall carbon nanotubes. Even people, they further bifurcate it in double layers and few layers carbon nanotubes. But obviously, this is basically a cylindrical hollow tube. So we call it one-dimensional structures where only one dimension is there and two dimensions are confined. We have then two-dimensional material, which is basically graphene, or one atom thick sheet. We call that hexagonal sheets of atom, which is basically we call it graphene. And yes, I told you that we can carbon nanoribbons, or we can call it that graphene nanoribbons, GNR in short we call it. So it is basically we are also doing the unzipping of carbon nanotubes, and then we are making these graphene nanoribbons. It is basically not exactly, you can say it is one dimensional, but yes, we call it quasi one dimensional structure, because somewhere we are just trying to confine one dimension of this material of this graphene sheet. So we are basically calling it that it is quasi one dimensional structure. And obviously all we know that about that diamond and graphite, which is basically a three-dimensional structure. So why we are talking about these carbon nanomaterials? It is because of the extraordinary and remarkable properties of these carbon nanomaterials. It is having very high electron mobility, high thermal conductivity, high current density, and you can find it in metallic as well as semiconductive nature. So it is because of these properties that you can use these materials, these carbon-based nanomaterials, particularly in transistors, transparent films you can use, LSI wirings, and there are so many MEMS and NEMS applications where you can use carbon-based nanomaterials. Then it is because of that high surface area, that strong absorption on the surface. You can use it for another particularly for energy storage applications, for fuel cells. You can use it for in supercapacitors. I'm also working in this area. I'm also working these graphene nanoribbons based electrodes, where I'm just looking for that to increase. I'm interested to get that high specific capacitance of that material, so I'm just working in that direction. So maybe very soon we will go for the results we have received, we will go for the publication. So then nanostructures, that is this material is very slim and strong. Means that mechanical strength of the material is very high. It is very lightweight, high thermal conductivity, very high physical strength, high electron. So it is because of these properties this material can be used. So there are, I'm not specifically going to particular applications because I have lot of slides, so I have to discuss, but a large number of applications. It is because of the extraordinary properties of these carbon-based nanomaterials, and particularly about these carbon nanotubes, and particularly about this graphene I'm talking about. So these carbon nanomaterials, this is basically, we call it an interdisciplinary material. As we have interdisciplinary branch, so this material is interdisciplinary, where this material can be used in material science. Physicists, they are using chemists, they are using mathematicians, they are using electronic people, biology, biochemistry, medical science. Lot of applications are there out of these carbon-based nanomaterials. Applications, if I talk about, so you can, as I told you already, that large number of applications you can use these materials in textiles. You can use them for energy purpose. You can use them for manufacturing of many devices, for ceramics, plastics, in sensor applications, for organ. Lot of applications of these carbon nanomaterials we have. So I'm just directly coming to this. So it is because of these extraordinary properties and the huge number of applications we call this material. This material is basically the materials of 21st century. Particularly I'm talking about these two materials because I'm working on these carbon nanotubes, and I think it is my own assumption, but I think maybe I am wrong, but more than 70% applications, in more than 70% applications papers, they are using these carbon-based nanomaterials nowadays. Somewhere they are using it, they are making composite with this carbon-based nanomaterials. And so two extraordinary properties as I'm talking about, two extraordinary carbon-based nanomaterials as I'm talking about, these carbon nanotubes and graphene. And carbon tube is a one-dimensional structure, graphene is a two-dimensional structure. So S. Izima, who invented this carbon nanotubes in 1991, and I got the opportunity when he visited the Jamia Millia Islamia a few years back. So I was there at that time. So I got the opportunity to interact with Professor S. Izima. So he's very nice person, and he's very clear-minded. Nowadays, he's working on various applications of these carbon nanotubes. So graphene, which basically we are going to discuss today about this. So this was Andre Ghim and Constant. So graphene is, I think maybe you are aware about it. It is a one-atom sheet, a planar sheet of sp2 hybridized carbon atoms that are densely packed in conformity crystal lattice. It itself consists of, if I talk about the graphite, because many of us we are aware about this material graphite. So it itself consists of many graphene sheets. They are stacked together. So if we are able to exfoliate these sheets, so then we would be able to synthesize the graphene. So, and there are various techniques I will just discuss about. If I talk about the carbon-carbon bond length in graphene, which is approximately 0.142 nanometer, and single layer graphene, which is having thickness that 0.345 nanometer. And you can see this is the HRTM image of a single layer graphene here. I have taken it from this paper. So if I talk about the structure, so different stacking arrangements you can have with this graphene materials: A stacking, AB stacking, and ABC stacking. And if I talk about its electron structure, so you will find that conical band structure, which is basically a zero band gap, which is having zero band gap, and that's why we call it a zero band gap semiconductor also. So properties, these are the, as I told you, that it is showing this material, particularly graphene, which is the strongest material ever, we are calling it. So this is this material is having very excellent properties. Thermal conductivity is 3000 watt per meter Kelvin. Theoretical thickness, we call it 0.345 nanometer. Single layer, the absorption is basically 2.3%. Zero band gap semiconductor. Resistivity 10⁻⁻6 ohm. It is having very high electron mobility, ballistic conduction is there. So it is because of these properties, this material is very promising material for various applications. And if I talk about the applications, so as I told you, some of the applications I have listed here, but as I told you that this material is having lots of applications, means almost in every field, in every area, this material can be utilized. So energy storage applications, so graphene-based supercapacitors are there, and I am also working on this. Although I am not working on this optoelectronic applications, I am working on the sensing applications. Ultrafiltration, I am not working. Composite materials we are making for other applications, for energy storage systems, and there are some biological engineering applications and photovoltaic cells. You can use this material in this photovoltaic cell. So if I talk about that synthesis techniques of these graphene and its derivatives, so you can use exfoliation and cleavage technique, epitaxial growth technique, Kummer's method you can use for the synthesis of graphene oxide and reduced graphene oxide. Chemical vapor deposition technique, which is basically, particularly if I talk about among the chemical, because thermal CVD, LPCVD, MPECVD, PECVD, there are a lot of families, I can say family members of this CVD technique. So particularly I will show you, discuss with you about this LPCVD technique and PECVD technique, and obviously unzipping of Cnts that can be used for the synthesis of, you can call it carbon nanoribbons, or you can call it graphene nanoribbons, so unzipping of Cnts. So we are also doing it. So I am basically working with this Hammer's method, with this CVD technique and unzipping of Cnts. So synthesis of, if I talk about particularly about the synthesis of graphene oxide by Hammer's method, the materials or the equipments which you will be required, that graphite as a source material, you will be required sulfuric acid, potassium permanganate, hydrogen peroxide, beakers, measuring cylinders, magnetometers, very simple things. And I think anyone can start with these few, means these are not very much costly. So you can start if anybody is interested in synthesis using Hammer's method. So here some points you need to understand, because a lot of people, or even my students here, they are working with, they are synthesizing two students. So sometimes they say, sir, we are not able to synthesize it. So because you need to understand a few points. If I talk about that concentration of the source material, particularly graphite, that graphite amount that used, which you are using for the synthesis, that is very important means point, because that oxidation penetration on graphite, that depends on the concentration of graphite in sulfuric acid. Higher the concentration of your source material, means this graphite, you are taking the graphite as a source material here, then lesser the penetration of oxidation, and concentration of sulfuric acid which you are taking, that higher the concentration of sulfuric acid, the higher the chances of complete exfoliation of graphite into graphene oxide. But you need to remember that very high chances of unwanted accidents. So you need to be careful when you are using these acids. Another is that role of potassium permanganate. That's this potassium permanganate that will act as an oxidizer, wherein the sulfuric acid that functionalize the graphite surface to add function in the reagents, like you are using here potassium permanganate. Therefore, the oxidizer should be added slowly, because it increases the temperature of the reaction, which may lead to the incomplete oxidation at the end. So remember, it should not pour instantly. You need to pour it very slowly, and it should be properly stirred using the magnetic stirrer. You can use for that. So another is that the DI water which you will use in this synthesis process, that rate which you are just adding that your DI water in the reaction. So rate at which water is added for the oxidation matters a lot. So it is suggested to add water drop wise very slowly to avoid unwanted accidents and for the synthesis of good quality graphene oxide. Role of hydrogen peroxide is also important. The main role of hydrogen peroxide is just to remove the excessive KMnO4. It is basically just to stop the reaction. So these are the and this is the I have taken this figure from a paper, Nature Review Communication, which are published in 2017. So this is the top-down approach and this is the bottom approach. So basically, top-down approach is you are just exfoliating the graphite sheets, and here in this bottom-up approach, you can use that CVD technique where you can just go for the bottom to top direction. Means you can just synthesize it using CVD. I will discuss with you that CVD techniques. So this Hamas method that was basically Hamas told it in 1958, but there are some other methods also, and you can use you can go for. But we are oftenly people, if you will just search, you will go you will search the literature, so you will find most of the papers using they have used Hammers method or maybe that CVD method. Because so advantage here, the most used method, large scale production is possible, medium quality graphene material is possible. Disadvantage that obviously that impurities and defects with this Hammers method you will obviously observe with in your material, and graphene of low electrical conductivity, large production of liquid waste. So these are some. Then this is I have discussed about that. Basically, when you will just go with these techniques, so you will get that graphene oxide. So now you will be required to reduce your material. So for that reduction purpose, you basically require that graphene oxide, obviously the material which you have just prepared during the previous which I have discussed here. You will be required, either you can reduce your material thermally, or you can use some chemical use for that as a reducing agent. So basically here because when you are using this Hammers method, so we are getting that powder, so we are using hydrogen hydrate as a reducing agent which can be used, and most of the papers I think you will find that they are use hydrogen hydrate as a reducing agent here. So but you need to understand that when you are reducing your material to that you want to get that RGO, means from graphene oxide to reduced graphene oxide. So you need to understand that the concentration of graphene oxide which you are taking, the main ingredients for this RGO synthesis is basically the graphene oxide. So in this case, you need to understand as much as concentration we take initially, that much amount RGO we get at the end of purpose. But you need to remember that much higher amount of graphene oxide can lead to the incomplete reduction, and thus bad quality final products you will get. So it is better you optimize the concentration so that you can get the good quality RGO. Another is that concentration of reducing agent or the hydrogen hydrate which you are using for the reduction purpose. That hydrogen hydrate that will act as a reducing agent in this method. So for this, you basically you have to optimize the reduction of GO, as I told you, that amount that is first, and then optimum quantity of hydrogen hydrate which you will use for the reduction purpose, that you also need to optimize that. And the another important point is that the temperature which plays an important role in that speeding up any reaction. So higher temperature synthesis will give us fine product high quality by consuming less time. So you need to optimize all these parameters, and when you will be able to optimize these parameters, so you will get definitely good quality material. So all these things you basically need to understand when you are using this means reduction for this reduction. You are going for that reduced graphene oxide using Hammers method. Another important technique which is very important here, that chemical vapor deposition for the synthesis of graphene. And synthesis of graphene is possible with this technique at very low temperature. I have worked a lot on with this technique. I have synthesized carbon nanotubes, single wall carbon nanotubes, multi-wall carbon nanotubes. In this single wall carbon nanotubes, I just want to tell you that I have particular optimization that I can get, or I can synthesize the carbon nanotubes of diameter, or the diameter distribution will be around 1 to 2 nanometer. So that PECVD system I have used. Yes, here it is important to mention that these PECVD or these CVD techniques which I am using, I am talking about. So we do not, we have simple thermal CVD here in Amity University, but these PECVD and LPCVD we have in Jamia Millia Islamia. So I have worked with under the supervision of Professor Mushaid Hussain there in 2012 or 13. So I'm continuously working in collaboration with now Professor Hussain sir. He is now retired. So Professor Zulfikar is there. He is in charge of these instruments. So he was my co-supervisor. So I'm continuously working in collaboration with Professor Zulfikar there. So these CVD techniques I have used a lot, and still we are using it for the synthesis of carbon nanotubes and high quality graphene. And here the main advantage is that you will get less impurities. Here in this purpose, in this technique, basically thermal energy of the system that will provide easier decomposition of the source gas. Here you will take a source gas. In this CVD technique, you will be required a source gas, and particularly if I specify that source gas, you can use methane or you can use acetylene. Mostly people they use methane, and we have also used with methane gas, and we have successfully synthesized these graphene. But if you are interested in the synthesis of these carbon nanotubes, particularly single wall carbon tubes and multi-wall carbon tubes, so you can use acetylene as a source gas, which is basically a hydrocarbon gas. So single layer graphene is possible at such a low temperature with this technique, and disadvantage is that obviously that the yield which you will get, which will be very low with this technique, and around 60% or something like that you will get with this. So so that is the CVD technique I was just talking about. So another method you can use, instead of using using that graphite, you can also use citric acid as a carbon source. And one of my students, he has also used the citric acid as a carbon source for the synthesis of pure graphene oxide. So citric acid can be used, and for this you will be required the sodium hydroxide, deionized water, magnetic shear round black bottom flask. You will be required beakers and some fine droppers. You will be required. Or the citric acid is basically the carbon source, hence the synthesis of this graphene oxide. We do not need graphite in this, as I told you, because here you are using the citric acid as a source material. So it has more than just one purpose. The far greatest one will be to produce the graphene oxide, because you will get graphite oxide from the thermolysis of citric acid. By neutralizing in alkaline media, for that alkaline media you can use sodium hydroxide, and it will turn that graphite oxide into graphene oxide. So another role of sodium hydroxide is to neutralize the liquid and just to bring the pH at 7. So this is the I have already discussed this part, that how you can synthesize that RGO from graphene oxide, and you need to understand all these optimization of graphene oxide, and the concentration of graphene oxide, or the concentration of or the hydrogen hydrate which you are using. And this is the basically flow chart I have just shown here. Yes, I just want to discuss a little bit about this CVD technique. As chemical vapor deposition techniques for the synthesis of graphene, it is very versatile instrument we have at GMI lab. Among various CVD methods, PECVD is the best technique for the synthesis of carbon nanomaterials, where you will use that plasmatic energy for the decomposition of your source gas. And as the source gas I am telling you, that is basically the methane gas which we are using. So it has following features. You can do the synthesis at low temperature. You will get a high yield in comparison to the thermal CVD, which means around 70% yield you can get with this instrument. Aligned growth of nanomaterials. You will get less defects. High purity is possible. Batch production is also possible. And another important point, which is the excellent reproducibility. You can reproduce the material with this instrument, because there is a automatic process control in the system. You just need to enter, or just to feed the recipe of the materials. Recipe means it is not that food recipe. It is basically that you need to that what is will be the concentration of your source gas, what will be the concentration of your this gas, what will be the ramp rate during the when the temperature will be increased, and what temp will be the maximum temperature, what will be the duration of that temperature, what will be the growth time. So everything you can just feed in the software, and all this system is attached with all the gases and some detectors. Everything is there, and you just, and there is an integrated process camera is also available with this. And I think you can see this blue part here on this right side. So this is basically the chamber, which, so here you can see, I will just discuss, I will show you the part of this system. So advantage of using this PECVD system, that synthesis of graphene is possible at very low temperature, as low as 600. Even I have used another I have optimize the growth even at 450 degrees centigrade or even 500 degrees centigrade. But if you will compare it with the thermal CVD, that growth, if you compare it with the thermal CVD, so you will find it at around 1000 degree or even more than 1000 degrees centigrade. So here plasma enhances the energy of the system, thereby early and easier decomposition of the source gas is possible with this system, and single layer graphene is possible at much a low temperature. So this is the beauty of this system, and this is the actual system which is installed at GMI, and we are using it for the synthesis of Cnts and even for the synthesis of graphene and its derivatives. And you can see all the detectors are attached with this system here, and this is the system, and this is this is attached with this. This is the chemical rotary pump, because the synthesis which we do with this system at around 10 to the power minus, it means that synthesis pressure is not as much low, but we can get with this pump, we can get the pressure at around 10 power minus 3. It is because it is a simple chemical rotary pump, you can call it. And the gases which you are using in this, with this system, so because these are the toxic gases, particularly that ammonia or hydrogen that we use for as a carrier gas. So there is a two-stage wet scrubber is attached with the system, and once that process or that growth process will be over, so those gases will come through or will pass through this wet scrubber, and then will go to the environment. So it is the main purpose just to remove the toxicity of these gases, so that it should not be the harmful. And this is the gas cabinet which is attached with this system, and in this gas cabinet we have these cylinders which is installed inside, and inside this cabinet also we have various detectors. So in case of any accidents or maybe any gas leakage, this is these detectors, they will immediately detect the very low concentration of the gas, and they immediately shut down the system, and that system will be stopped completely, and all the gases, they will be stopped completely immediately. This is the versatile instruments we have here. So this is the synthesis of graphene oxide. This is basically the chamber, and I just want to discuss about the recipe which I was just discussing about that. For the synthesis of graphene oxide and its derivative using this CVD system, you will be required a catalyst coated substrate, and here our substrate is silicon. On we use copper, or you can also use nickel for the preparation of thin film, and for the preparation of thin film you can use RF sputtering technique. You can just make a very small, very thin film, means and that should not be, that the thickness should not be very much high. So you have to optimize with that, and you can put, then when your catalyst film is prepared, you can put it in the quartz bale jar, and you can just go for the pre-treatment, and pre-treatment for 10 minutes at these are some optimized parameters I have listed here. I think any one of you interested, you can just note it down for the synthesis of graphene oxide using this technique. This is the growth time, around 15 minutes. DC pulsed flow discharge plasma 40 watt was used during the growth process. So another important point is here the characterization of the material and its derivative using, I have just mentioned here 2 or 3 techniques: electron microscopes, XRD, and Raman spectroscopy. You can use it is, sorry, it is Ramans, not Ramans, it is Raman spectroscopy. So these are the SEM image and TM image of our samples, which were we have cloned with this PECVD technique. So you can see that some layering pattern, because it is a film, thin film. So that's why we are getting this uniformity. And this is you can see, if you will go for the higher resolution, you will get its continuous undulating layers. And we have gone for this TM characterization, and this is the, we are calling it that these are some single layer graphene, these are some few layer graphenes. It is basically with the help of this, because this is no HRTM, we have simply used TEM, normal TEM. So we could not optimize, so we have gone for the confirmation. We have used Raman spectroscopy. You can use whether it is a single layer, whether it is a few layers. So obviously, when we have grown this, so it is with this system, even it is not, I think maybe some of you are working on this graphene using that Hammers method. It is not possible to synthesize the graphene, single layer graphene with the Hammers method. But even yes, people they are using some treatments, they are growing, but it is means possibilities are more if you are using this PECVD technique for the synthesis of graphene. These are the graphene oxide grown by Hammers method. I have shown you here, and you can, for further confirmation, you can just go for the XRD and Raman spectroscopy. These are the, yes, this is the which I was just talking about, these nano ones graphene. So we have synthesized, these are this is our actual picture, and we have using that unzipping of carbon nanotubes, we have synthesized these graphene nano ribbons. And here we have one more control with the length also, because you know the length of the CNT is in micrometer. So with our method, we have optimized that how we can further cut the length. So we have also tried to do that, and this is really, I think, some only few people in India they are working with this carbon graphene nano ribbons. They are working with this material. You can find lot of papers. They are totally based on the theoretical calculations or theoretical models. So Raman spectroscopy, that is very powerful technique, or that is the best technique you can use for the qualitative analysis of your material and its layers. And if you want to identify your material, whether you are having that single, double, or few or multi layers, so you can identify it by the peak position or peak intensity and peak broadening of the spectra. And these are some I have, although this is not my graph, I have taken it from a paper. I have just already given that reference. But if you can just go for means for the identification whether it is single layer, in that case, if you can just calculate the ratio of I2D upon Ig, if it is around 2, so you will get that it is single layer. Although there are further information, you can get it from HRTM or some other techniques. Even for with that AFM, you can do the confirmation. Or double layer, if you will see that if you will calculate this ratio I2D by Ig, so you will get it around approximately 1. So in that case, it is double layer. For few layers, you can see that the intensity of this 2D peak is basically reduced in that case, and it is higher. So it is I2D by Ig it is less than 1, around 0.8. So you can call it few layer graphene, and for multi-layer graphene, you will see that I2D by Ig. So the number of layers you can identify by seeing the observed G band position in Raman spectra. This is one. Another, you can calculate the intensity ratio of 2G by G peak in Raman spectra. And third is that intensity ratio of D by G peak in Raman spectra. I think you can see that we have also in this graph, it has also been this calculation is done there. So in our case, Raman spectra of graphene, so we have also observed these. These are basically characteristics peak. If I talk about these peaks, so you will find basically various. These are characteristics. This D band is basically it will show you the disorder band. We call it disorder band, or you can call it defects band, and it represents a ring breathing mode from sp2 carbon rings. So basically, if it is simple indication, if the band is typically very weak in graphite, and it is typically weak in high quality graphene as well. If this D band is significant, it means you have a lot of defects in your material, and the intensity of this D band is directly proportional to the level of defects in the sample, you can call it. If I talk about this G band, so G band is basically the we call it the graphitic band. You can it is basically a sharp band. You would usually observe this band somewhere around 1585 centimeter inverse, somewhere around in the spectrum of that graphene. And this band is basically is an in-plane vibrational mode involving that sp2 hybridized carbon atoms, and that comprises the graphene sheet. So this basically this G band position is highly sensitive to the number of layers which is present in your sample, and it is one of the best method for the determination or for the identification of the layers, and it is based upon the observed position of this band for a particular sample. So basically you can use these techniques for the identification of the layers of your. We have also done this characterization. Yes, we have already published this paper in Applied Surface Science. I need to mention it here. So these results are already published there. So you can just go through and can search the paper, and can I think if you want more details, you can go through this paper. So high resolution scanning probe microscope, which we have used, and with the help of line profile done with this instrument, we have tried to optimize the or to calculate that layer steps, and it is we observed that the layer steps is around 0.5 to 1.75 nanometer, much larger than which is basically the theoretically it has been written that it should be 0.156 if it is means these layers are stacked with each other. So this is basically the distance between two graphene layers of multi-layer graphene. So we can say that we have synthesized loosely stacked because this steps thickness or this gap is too much. It is more than this. So we are saying that these are our loosely stacked single layer graphenes. XRD is another tool which can confirm the synthesis of your material, and this also the existence. It will confirm you the existence of 0 0 plane of the graphene, and you will find it somewhere around 24 degree to 26 degree. You will find that you will search the literature, you will find it somewhere around there. Then we are also using, as I told you, that synthesis of graphene-based nanocomposites. We are working on this, and these are the silicon nanowires and graphene nanocomposites which we have synthesized here. These are some pictures. I am not going to detail because I think time is almost, it is 11:24. So these are the TM images. This work we are also doing here, and we have used this. I will show you some sensing results of this composite structure. But before that, I just want to discuss about that these carbon nanomaterials they can be used in various types of sensor applications, and particularly if you talk about pressure sensor, flow sensor, stress strain sensor, thermal sensor, gas sensor, optical. So we are basically working on these gas sensors, and one of my students is also working on these biosensor. So if I talk about the sensor parameters, particularly about if I talk about that so gas response or the sensor response or sensitivity we call. So the most essential parameter of gas sensor is its response, that how responsive is how much your sensor is responsive so to your target gas. Or so in that case, so if you talk about that response is generally defined as the ratio of that resistance variation is Ra upon Rg, or you can call it Rg upon R, where Ra and Rg they represents the resistance of your gas sensor in air, and that in the presence of your gas. So therefore, if you want to calculate the response of a gas sensor, you will calculate this ratio, and its resistance in air and the target gas should be continuously measured. If you talk about the sensitivity, it is the change in measured resistance delta R with the change in analyte concentration, and with the help of the slope of calibration graph, you can calculate the sensitivity of your sensor. Response time you can calculate. These are some characteristics parameter of your sensor which you need to calculate when you are working in this sensing applications. Rapid response and short recovery time are always preferred owing to the. So if you are making a sensor and you are so obviously that response time should be very less, means immediately if there is any leakage of any gas, of any toxic or explosive gas, immediately it should respond. So that response time should be very less. So in our case, I could not mention here that data, but we have very recently worked on some ammonia sensors. We have worked upon that carbon monoxide sensors. We have worked upon that NO2 sensors. So in our case, and another important part which I will discuss, that recovery time, that is also important, because your sensor should recover back to its original state without, if it is possible, without any external energy source. That I think it is the best sensor. So in most of the cases, we have recovered our sensor at room temperature without the supply of any external energy source. I will just show you. So recovery time is defined as the time needed for the resistance of a gas sensor to return to 90% of its original baseline value after the removal of the target gas. And a good strategy to improve the response and recovery of the gas sensor is the use of porous structure, which provide abundant channels for the diffusion of gas species. Selectivity is another important part, that how selective is your sensor. It should be selective for a specific target gases. It should be selective. So that is another important part, that linearity, what is the LOD, limit of detection. So these are the results which I was discussing about, that we have observed in one of our case, that and you will see that it is 150 or so. Here that response time is very less. I think it is 5 to 7 seconds. It is responsive, but obviously recovery time is quite more. And here the response you will find it this is around 1.32, something like that. And this is at different concentrations, at 1 ppm, 0.5 0.1 ppm, 0.5 ppm, 1 ppm, and this is the repeatability of our sensor. So this is all about the graphene, its characterization, and sensing applications. Do I have? Can I continue? I have time, Parshal sir.
Yes, you have time till 12 o'clock.
Okay, okay. So I just want to discuss a little bit about that carbon nanotube. Although it is not two-dimensional, it is a one-dimensional structure. But I just very quickly, I just want to discuss about this material, that these carbon nanotubes, you can get single wall carbon tubes, multi-wall carbon nanotubes. And as I told you that Ijima was a scientist who discovered it in 1991, and later in 1993 he discovered single wall carbon nanotubes. It is basically a byproduct of that fullerene, which has a closed carbon structure. And if you simplest way you can call it, if you roll up a graphene sheet into a seamless cylinder, then you will get that carbon nanotube. So we are doing the both things. We are basically synthesizing these carbon nanotubes by rolling that graphene, and we are unzipping it to make it graphene. And the best known fullerene is C60, that consists of 12 pentagons and 20 hexagons. But in case of this CNT, which is basically a tubular structure, and here the structure is spherical, but here in this tubular structure, the carbon nanotube, it is having 6 pentagons and required 6 pentagons are required. Here it is 12 pentagons, but here it is 6 pentagons are required to close the CNT. So CNTs are holographic coaxial cylinder of few nanometers in diameter and few micron in length. So CNTs, they are made of graphene sheets. They can be single 2D layer of 3D graphite. So if I talk about the properties of these CNTs, they are having very high mechanical strength. They are 100 times stronger than steel. And electrical conductivity 6 order of magnitude higher than copper. And I'm just going through very quickly, because I have discussed about this CNTs. So I just thought okay, I should discuss about these CNTs also. Thermal conductivity is also quite, it is 5 times more than copper, and it can be functionalized to enhance the absorption on the surface, or for the requirement of various other applications. Depending upon the number of graphene sheets present, CNTs, there can be single wall carbon tube, they can be multi-wall carbon nanotube. They have a cylinder. If I talk about the single wall, so they have a cylinder cell with only one atom in thickness. Electronic band structure is less complex. If I talk about, they have multiple coaxial cylinders of increasing diameter about the common axis, but here in case electronic band structure is more complex if we compare it with. So here the main important point is that you can it is not easy to synthesize these SWCNTs, but it is easy to synthesize MWCNTs. But if you talk about that electronic band structure, so it is here in this case it is complex, and it is not that much complex. So I just want to discuss about the synthesis part of, because I think yes, growth of carbon tubes. So for this growth of these carbon nanotubes, you will be required, you need to first select the wafers, means particularly the which orientation will be supported or which will be useful for the synthesis of. So in our case, we have used silicon as wafers a lot, but you can use molybdenum and aluminum wafers also. 2-inch diameters we have used silicon wafers, which is hydrophobic orientation, having orientation 110 and 100. So we have used these one. And nanotubes grown on silicon are in general much longer than those on silicon. So these are our optimized parameters. And when I was in Jamia, so a few years back, so I have worked a lot and I published a lot of papers on these. So cleaning of wafer is another important, which is important part when you are going to synthesize the carbon nanotubes, particularly with the CVD technique. So you need to understand that wafer cleaning is. So if you can clean it using acetone, and you can use ultrasonicator for that, and and another is that you can dry it, and dry part is very important because you need to dry it in vacuum, or maybe you use nitrogen gas for that drying purpose. So RF sputtering you can use for the catalyst preparation. As I told you, I discussed with you, even for the synthesis of graphene using PCVD technique, you will be required RF sputtering technique for the catalyst preparation. So this RF sputtering system you can use, and you can make a thin film on silicon wafers. You can use this technique. So we have, as I told you, that we have at Jamia this LPCVD system also. And initially, when I was doing PhD there in Jamia, so I have used this system and it was installed in front of me. So these are the growth conditions basically which you can use here. That gases, this NS3, ammonia, and hydrogen, these are the carrier gases. And as I told you that this acetylene you can use as a source gas for the synthesis of your carbon nanotubes. So this is the flow rate of, or the how much flow you should keep when you are using this LPC. This is basically a simple thermal CVD, but there is a extra provision of that vacuum. You can see here, this is the rotary pump attached with this system. So this is simple rotary pump. You can attach, you can get the pressure of the order of 10⁻³ torr. But you generally, when we use this system, so that much pressure is not required. So you will be required only up to means somewhere around 100 millibar or 200 millibar. So temperature, these are the growth temperature. You can use 600 degrees centigrade to 700 degrees centigrade, but you can see that if you compare it with the PCVD system, here the growth temperature is little bit more, but in some cases it is even more than 1800 degrees centigrade. So we have optimized these parameters and time the growth. This is basically the growth time. So we have kept it at 5 to 20 minutes. So it means you can optimize. Another, I just want to discuss here one thing, that it is not, these are the parameters which I am sharing with you, but that these parameters you need to optimize at your place, because temperature, humidity, means that working conditions, these are very important when you are working on these carbon based nanomaterials, or for the synthesis of these carbon based nanomaterials. So you need to optimize at your place. But yes, you can keep these parameters, and I think somewhere you can just optimize. So when the temperature is 600 degrees centigrade, then we allow to flow this hydrogen and this ammonia gas. They are the carrier gas. Then the mixture of hydrogen screen was allowed to flow into CVD chamber for a desired time, means 5 to 20 minutes. This is the system, which is basically from Taiwan. And these are the SEM micrographs which we initially we have grown with this system. And this is the scanning X-ray microscope there at Jamia. And this is a single wall carbon nanotubes which we have grown with this LPCVD system. So these all are the images which we have grown with the help of this LPCVD system. So I just want to go further and just want to discuss about single wall carbon nanotube. Single wall carbon tube, these are the growth parameters. And as I told you that it is not easy task to grow these single wall carbon tubes. So PECVD system, we tried a lot. We were successful with the system also, but the purity and the yield which we were getting with that PE CVD system, it could not be possible with this LP CVD, normal thermal CVD system, basically. So these are the pre-treatment conditions you can use for the synthesis of carbon nanotube using PE CVD system, and these are the growth conditions which you can use for the synthesis of single wall carbon nanotubes. Two or three things are growth time is important here, that you need to keep it 10 to 20 minutes in between this you can optimize, and pre-treatment is also important, because and here it is another important point that I have not used ammonia here in this case for the synthesis of. We have used only hydrogen as a carrier gas. These are the our grown structures, grown single wall carbon nanotubes with this PEC system, and this is the RBM mode basically, or the Raman spectra. Here we have, you can calculate that even diameter with that 248 by nu, so that nu is the basically your Raman shift. So if you will to divide it 248 by this 218, so you will get that diameter. So somewhere you will get around 1 point something diameter, and these are the growth conditions. So at different conditions I have optimized during my PhD time and when I was in Jamia. So these all are the different conditions, and these are the Raman spectra conditions, and that you can see that surface morphology of our grown tubes. These were basically vertically aligned tubes, and these were basically horizontally aligned carbon nanotubes with so obviously growth conditions, pre-treatment conditions, yeah, these are different for so you can depending upon your applications, you can synthesize the carbon nanotube with different orientations, is vertically aligned or horizontally. You can grow these structures. These are the high resolution TM images of multi. This is the single wall carbon tubes. Here it is basically for this multi wall carbon nanotubes, and we have grown these pictures or these multi wall carbon tubes with this PECVD system, and we have just patented these structures, and we can grow it. We have set parameters for the synthesis of these. On the tip you can see this is the basically catalyst, and we have used nickel catalyst for the synthesis of these carbon nanotubes. So this is the Raman characterization of these systems, Raman spectra. Raman characterization you can do similar for this, means as I told you, this Raman spectra is a powerful technique for the identification of your means even for the identification of whether it is single wall carbon tubes or whether it is multi wall carbon tubes. So you can identify in the single wall carbon tubes, you will get the relay breathing mode, where you can also calculate the diameter of your tube. But in the case of multi-wall carbon tube, you can identify that using that D and G peaks. You can identify the ratio. You can calculate, and you can calculate the how much what is the quantity of diffractions you have in your structure. So these are the Raman spectra in our tubes. These all are the Raman spectra. So we are working these CNT and graphene based gas sensors, and they have shown very. This is our work which we have recently published in AICTE Materials Research Bulletin. We have published it. These are our device which we have made, and these are our sensing response. We have done this calculation for different horizontally aligned carbon tubes and for vertically aligned carbon nanotubes. These are the repeatability of our both set of sensors, means for randomly oriented SWCNTs and for vertically aligned SWCNTs. And this is the histogram shows the error bar here and nature of the sensor response versus with the concentrations. You can that so in our case that 2 ppm was the our limit of detection is the LOD. Stability we have measured, calculated for our sensors, and this is another paper where we have decorated our CNTs with gold nanoparticles, and then we have used it for the sensing applications. This paper is published in Sensors and Actuators in 2018, and these are the sensing results. These are our, we have functionalized our carbon tubes, and these functionalized carbon tubes. Then further we have yes, another work we have done with the plasma functionalization we have done. So different groups we have added with that help of that plasma functionalization, and we have used it for that field emission applications and then for sensing applications. So these are our founder president, Dr. Shakra Chauhan, founder president of the Amity University. He's very much dedicated, and he always inspired to work day and night. So he always helpful for any kind of support. He is always there, and I think you all are aware that we are at number one, Amity University at number one, who is filing patents, and a lot of patents have already been granted. So then our professor, our director, Professor Dr. V.K. Jain sir, he is always motivators, and Professor Hussain, he was my he's my guide basically when I did my PhD. Now he's retired. Professor Zulfikar is there. Professor Abhishek Verma is here at Amity University, and Dr. Dasmanaji and Dr. Samina Hussain, she is working there. So these are my Samina Hussain and Professor Zulfikar sir, my collaborators. They are working here. In a lot of applications. They are my PhD students, Varsha Gautam, Shalvi, Sonia, Pooja, and this is the product student. These two are, they are working in the different projects. So that's it. These are our recent publications which we have published basically to 2020 onwards. So these are our recent papers. Some papers on sensors, IR sensors, graphene composite bit sensors, IR sensors. So these are some papers recently published in 2020 and 2021. Thank you very much.
Thank you, Dr. Avshish, for the nice introduction about how to start with graphene synthesis, and then as a whole the overview up to application point of view. So it was nice. I see some questions in the chat box. So can you read it, or shall we read for you?
Yeah, just a second, sir. Okay, I will take it from here. Swati, can we do some work when the lecture? Okay, please click. Okay, the question initially.
Jignesh Kumar, he asked, how can we reduce response time for sensors to sense gases quickly?
Response time you can reduce. Basically, it depends on that how fast is the absorption of your analyte of your target gas with that with your material or with your sensor. So you can just you can increase this response times. You can function. You know, I told you that you can. It would be in some cases, and we have done that study also, that defects, they are more crucial for the means absorption, and people they use they functionalized with different means carboxylic group or subnitride groups, and then they also functionalized it with some metal nanoparticles to enhance the absorption. So if when the absorption will be fast, so means that response times, obviously that depends that how fast is that absorption with the surface of your sensor. So that depends on that. So you can accordingly, depending upon the analyte or the target gas which you want to use, you can enhance that. You can functionalize your material, your material, particularly if maybe you can use if you are using on that metal oxides, so you can add the main purpose to make the nano composite. It is basically that we want to increase or we want to enhance these sensing parameters. Although our RGO and simple pristine RGO and simple pristine CNTs, they are also very good. They are also responsive for our target gases, but particularly if you want to enhance, so you need to optimize or you need to check that which target gas you want to use, and accordingly you can functionalize your material, maybe with some metals or maybe with some carboxylic or nitride groups, or you can attach some other some other materials, and then you can enhance it.
Dr. Ashok Kumar, he want to know, could you please tell me the process of graphene thin film deposition?
I have already discussed that PECVD and NPCVD technique, so that is there. PECVD technique, and if you want to discuss more about this technique, then you can give my number, so I will exact parameters what if you want to optimize with your CVD system. Maybe you do not have that PECVD system or LP system. If you have normal CVD, then you can grow that thin film of your graphene. Yes, if you are synthesizing it with that simple means Hammer's method, so you can make the thin film of your you can just make the solution. You can find the suitable solvent of your this material, and you can just disperse it using ultrasonic bath, and you can simple people, they are using drop casting method, spray pyrolysis method, or spin coating technique. Although it is better to use that drop casting, it is very simple and method, drop casting, or maybe if you have that availability of spray pyrolysis, then you can use that method also for the thin film deposition of your material.
Jignesh Kumar, he wanted to know what was the diameter of carbon nanotubes obtained by you.
In case of single wall carbon tube, as I told you that we have synthesized the carbon nanotubes with diameter. In case of single wall, our diameter was 1 to 2 nanometer. We have that specific parameters. You can optimize those parameters, because there are so many things when you are synthesizing the carbon nanotubes. It does not depend simply. I can just tell you the recipe, as I told you, that temperature, what is the working conditions, and what is the purity of your catalyst film which you are taking, what is the thickness of your film. There are so many parameters on which your the diameter of your material will depend. So you can optimize. As I told you, I have worked a lot, and I have that optimization. So more details you want, you can go through my papers. There are a lot of papers. You can simply search in Google Avshish Kumar carbon nanotube. So you will find a lot of papers which I have published, and even you can call me and we can discuss if you want to discuss more about that.
Dr. Sundaram informed, excellent and inspired lecture, sir. Thanks a lot, dear sir. We synthesis geo using Tour's method. We got exothermic reaction. What are the steps to protect from such kind of exothermic reaction, except fume hood?
Actually, I have not used, or my students, they have not used this Tour's method which you are talking about, but that can be the one solution, fume hood, that you are saying. I don't know why you are not saying that it should we accept fume hood. But I think it is better. You can use simply the Hammer's method, and I have shared with you, I think, in more detail that what can be the parameters and what you need to understand when you are synthesizing the material, is what are the factors which can affect your synthesis. So I think this is the simplest method, and if you want more purity and more yield of your material, you can go for the CVD technique. So I can help you if anyone of you are interested, so to get the high purity carbon nanotubes.
Dr. Manohara, he wanted to inform you that we have synthesized few nano composites. Is it possible for doing sensor work of these on collaboration basis?
Sure, most welcome.
Then
Most welcome. You can
Dr. Swati Mehra, sir, which method you find best to synthesize and you got good results as per your expectations?
Actually, that depends on the availability of I have compared, I have discussed both the techniques. I have discussed that this chemical, simple chemical route is the Hammer's methods which you can use for the synthesis of graphene. I have also discussed with you that CVD techniques, and on these two, obviously CVD technique is the best one, but it depends. You may not have these facilities, means the PECVD, LPCVD. Even I do not have here in Amity, but I am working in collaboration with still. We are able to synthesize. So it depends on what facilities you have. So even you can synthesize good quality material with the means Hammer's method. You can further go for the purification. If you are getting means impurities, you can further go for the purification. And I have already discussed so many parameters what you need to take into consideration when you are synthesizing the material. So it depends on that. But CVD is the best. Yes, sir.
Okay. So, Pradeep, sir, do you have any idea about MOS2 materials and COMSOL, COMSOL tool? I want
I
to
have
know
not.
that using MOS2 material, using COMSOL tool. Can you please suggest any idea?
Actually, I have not worked on that MOS2 tool, but I can help you. One of my friend, he is working with this material, so I can. Means if you want any help, so we can discuss, and I can maybe it may be useful for you. But I have not worked on this MOS2 material.
So, I don't see any other questions. So, thank you very much, Dr. Avshish, for sparing some time and sharing with us about your activity. It was nice, your presentation as well as interactions, and hope in near future also we will have you with us in other programs. Thank you very much.
Definitely.
And participant can contact him. His email ID is there in the websites, or if you want. So thank you very much once again. Thank you, sir.
Thank you, sir. Thank you, sir. Thank you very much for providing me this opportunity so that I can share my work. It is really a very good platform and this rugby development program. So it is really nice, sir, to be the part of this program. So, and I hopefully, I hope that in near future, I will participate in some more programs. Thank you very much, sir.
Okay,
Hello,
sir.
hello. So this is
Please,
Dr. Kumar from Siddhaganga Institute of Technology, Tumkur, Karnataka. Hello.
Yes, sir. Yes, sir. Yes, sir.
so Dr. Avshish, can you please unshare your
Yes,
slide?
sir. Okay, sir. Thank you, sir. Thank you very much. Okay.
Our next speaker is Professor Samir Sapra from IIT Delhi. So he will join with us, I think, in minutes, and we will start from 12 onwards. So let's wait a few minutes. So good afternoon, Professor.
Good afternoon, sir. Good afternoon.
So I welcome you here in this program. So
Thank you.
thank you very much. So we will start in minutes. So are you ready?
Yeah, sure.
Okay. So time is 12 o'clock. Still maybe 2-3 minutes.
I can wait. No, not an issue.
Yeah. Or we can start. No
Whatever
problem.
you prefer.
Because all participant is here, so we may continue.
Okay.
So Surajit, yeah, please.
Very good morning to everyone, participants and resource person. We are at the session 4, the second session of the day. So this session will be led by Professor Swami Shakra. Professor Swami Shakra is a professor in Department of Chemistry in IIT Delhi. After completing PhD from Indian Institute of Science, Bangalore, he was postdoc fellow at LMU Munich and at TU Dresden. Professor Sapra's research of interest are material science, nanotechnology, quantum dot, charge separation and extraction, photocatalysis, photovoltaics, etc. Professor Sapra has published more than 100 research articles, 4 book chapters in internationally recognized reputed journals. Professor Sapra completed total 5 research projects funded by reputed funding agencies like Department of Science and Technology, Government of India, DRDO, etc. Professor Sapra was awarded with some prestigious awards like Outstanding Young Faculty Award by IIT Delhi, Alexander von Humboldt Fellow by AVH Germany. So I would request Professor Sapra to kindly take over the session and present your presentation. Thank you, sir.
Yeah. Thank Dr. Sen for a very generous introduction and for inviting me to talk at this program. So let me share my screen. And how should I go about it, Professor Hussain? Tell me.
Sorry?
How do I go about it? So I talk for 1 hour and then half an hour for questions and then the exam session?
You have to tell 1 hour 30-minute sessions. It's for presentations and interactions because participants are mainly teachers from college and university.
Yes.
So they will interact and exam we will conduct at the end of the program.
Oh, okay. So, okay. So what I suggest is that instead of waiting till the end,
yes,
if you have any questions, then you stop me and ask me. Okay. Yeah. That will be the best way we can then interact.
Okay, then participant can.
You can stop me at any time. You can ask me. Yeah.
Sure.
All right. So let me share my screen. One moment. Yeah, I'll not be looking at the chat box. So just ask me by unmuting your mic. All right. So is it visible now?
Yes, it's perfect.
Just a moment. All right. Some problem?
Yeah, it's okay.
Okay. All right. Okay, so, well, now it's almost good afternoon, yeah, everybody. And what I'm going to talk to you about is essentially some of the colloidally synthesized two-dimensional nanomaterials, and I'll tell you some basics of that and some applications. Yeah. And since this is a program on these two-dimensional materials, I'm sure that there'll be a lot of repetition in what I'm going to talk today. Yeah. So I can perhaps move on. All right. So if I yeah, so let me tell you that I have a web page where you can see my latest research activities, and also you can email to me whenever you have any questions or anything that you wish to ask. So let me, at the very outset, acknowledge the people who've done this work. In particular, Shamim, whose PhD work is what I'm going to present today. And later on, Ajit, Sahil, and Varsha are continuing some aspects of this work on 2D nanomaterials. And also, I must thank my collaborators, Praveen, Ritu, Shashwata, and Shamit, who've helped me with various activities of all these projects, right? And the funding agencies, DST, DRDO, SERB, and definitely IIT Delhi. We have a very good central research facility at IIT Delhi, which is open to everybody, by the way. So if you have any samples that you prepare, or if you want to make any devices or do any measurements, everybody is more than welcome to come and use them. And everything is online, so one doesn't have to contact anybody, but just fill up the forms online. So I encourage you to look at CRF, Central Research Facility. All right, so coming back to my talk, most of the time that we spend is we keep thinking about energy, how to convert energy, be it solar cells, hydrogen generation, fuel cells, how to store energy, how to utilize this energy smartly so that you have minimum waste, and how to clean up the mess created, right? You need to do a lot of regeneration, photocatalytic degradation, conversion, carbon dioxide removal, so on and so forth. So these things highlighted in the green are the kind of activities that go on in our lab. Okay, and I'll definitely pick up a few of them to show you some of these results. Right. Most of our activity is centered around these nanomaterials. Okay, and in particular, I'm showing you a picture of cadmium selenide quantum dots. And these are all cadmium selenide, but different sizes of quantum dots. And by just changing the size of the quantum dots, you can change the fluorescence emission color, which is shown over here. I'll discuss a bit about this in a later slide. So these nanomaterials are very, very small, right? The nanosheets are indeed much smaller, but typically our nanomaterials are within 5-6 nanometers. That's typically the maximum thing. Okay, maybe 10 nanometers, some of them. Since we are working with semiconductors, we don't go beyond those sizes. So we study a lot of surface property relationship. Okay, size property and surface property, because a lot of atoms happen to be on the surface of these materials. Okay, so we see these quantum size effects, which I just briefly told you about. We see how different crystal structures can be made from the same material. We explore a lot of new synthesis methods. And, you know, each of these nanoparticles happens to be different from the other one. So you also need to do a lot of these single particle experiments. You can see these things blinking over here. Yeah, some of them are green colored, some of them are red colored. So those kind of things. For the past 7 years or so, we've entered into something called photovoltaics, and also the associated field of photocatalysis. So we make some of these very simple devices in our chemistry lab. For example, the dye-sensitized solar cell, DSSC, or the quantum dot sensitized solar cell, or we've also started with the perovskite solar cells. Okay, and with photocatalysis, and also electrocatalysis, I'll come to later. We also explore water splitting, for example, making hydrogen or making oxygen out from water. All right. Then, of course, there are these very lovely perovskites, which have taken the scientific world by storm since 2009, when Miyazaki first discovered that they have a good application for solar cells. Yeah, although it was not stable, it was like 4 or 5% efficient, but there were these perovskites. And within a span of 2 to 3 years, the efficiencies increased. Now you have 24%, 25% materials available. The stability is still an issue. Lead toxicity is, of course, an issue. So we explore a lot of these layered or double perovskite materials which are lead free. Okay. And then LEDs. We focus a lot on white light emitting devices in particular. I mean, we do focus on various different emissions, but if you see, you can tune the white light from bluish white to yellowish white, and therefore in the market what you know as cool daylight or warm daylight conditions. So you can get all these different LEDs fabricated over here. We worked a lot on sensors based on these nanomaterials, biosensors, ethanol sensors, sensors, gas sensors based on transistors. And for example, this is an example of biosensor. Okay, so you have these nanomaterials and you have DNA strands over here. So you take a single stranded DNA, okay, and already, for example, we work with chronic myelogenous leukemia, CML for short, okay, blood cancer. And you take a DNA strand which has a sequence of this CML, okay, and it's a unique sequence. Now, when you take a sample from the patient, that person will have the complementary strand over here, and that comes in base pairs over here. Okay. Along with that, you put a redox agent over here, and you'll find a lot of redox activity, due to which you'll have changes in the current levels. So these are amperometric sensors over here. Okay. Likewise, we have a lot more sensors that we've developed at various stages of our research. And of course, these nanomaterials have found their way into these poor mice. Well, for example, you see over here, there are nanomaterials which are fluorescent, and there are nanomaterials which are magnetic in nature. And you can take them to any part of the mice and image all these cancer activities or other things, whatever you want to. By the way, all these things shown in yellow have a very strong collaborative effort, okay? So, for example, we don't fabricate the LEDs in our lab, or we don't fabricate the sensors, or we don't do any animal studies in our lab. And these are all with strong collaborations that we've done. The things that I'm going to speak today are these two-dimensional transition metal dichalcogenides, okay? For example, molybdenum selenide, molybdenum sulphide, tungsten selenide sulfides, tellurides. So these are the kind of materials which we are working with, and these are sheets, okay? And then how we modify these sheets, how we make heterostructures of these sheets, how we make use of these sheets for various applications, including photoconductivity, including catalytic activity, so water splitting. I'll show you some of these things today. So this is the brief outline of the talk. A small introduction, okay, and then I'll show you some applications, some properties of 2D transition metal dichalcogenides. So photovoltaic, photoconductivity, catalytic applications, to sum up all of them in no particular order. And yeah, then we'll summarize the talk. And again, if you have any questions, any doubts, shoot. So let me tell you something about molybdenum sulphide. Okay, some facts about these. The most naturally abundant is the 2H polytype. Okay, and it has been used for quite some time, in particular for dry lubricants. This is a layered structure, MOS2. Okay, much like graphite. So, you know, graphite also has a lubricating property. So, in certain few catalytic reactions, or for lithium-ion batteries, okay. But since the advent of these graphene materials, where the Scotch tape method was used to exfoliate, what you do is you put a Scotch tape, you exfoliate, you do that again and again, and then at the end of it, you expect that you'll find some monolayers or some few layers. So 2004-5 is the time when graphene came in, right? And since then, the number of papers in these materials has grown enormously, and because one could make 2D materials of the transition metal dichalcogenides. Okay, and then several new applications have come in. All right, other than the traditional applications of molybdenum sulphide that were already present. So to tell you something about MOS2, it's got a direct band gap of 1.9 electron volt from single layer molybdenum sulphide. Otherwise, it's an indirect band gap material. Okay, so the good thing by having MOS2 is that you fill your complete kitty. So you have conductor, you have an insulator, boron nitride, and now you have a semiconductor. So any kind of application is possible. The good thing with 2D materials is that it's flexible, it's transparent, okay, and so you can think of the low power devices. Also, the good thing about 2D materials is that it has a lot of surface, so you can think of a lot of catalytic activities. Okay. To tell you about the structure of this material, and there are these three different kinds of structure: 1T, 2H, and 3R. Essentially, what you have over here is a 1T, a tetragonal structure, hexagonal structure, or a rhombohedral structure. And this 1, 2, and 3, what it means is that one monolayer of the transition metal dichalcogenide, for example, the gray atoms over here depict the molybdenum atoms, and the yellow-orange ones depict sulfur, okay, so the chalcogen atom. So just one monolayer completes a unit cell. In 2H, since the packing is not exactly one on top of each other, so you need two monolayers to complete the unit cell. Okay, there's a hexagonal packing like the AB packing. Okay, so ABA and BAB, these are the two things that are there. And in 3R, of course, you need three monolayers, and that's the rhombohedral case. Okay, and of course, you can have a lot of distortions also. I'll tell you a bit about distortions, but first let me just complete the structure. Okay, so if you know that only 2H and 3R are stable and they are found in nature, okay, yeah, this I've told you. The distances are typically, when you look at these materials again, you'll see that between the planes, the distances are smaller compared to the interplanar spacing, and these interplanar layers are because of van der Waals interactions. Okay, so these are weaker than the intralayer covalent bonding. Okay. 1T has an octahedral coordination. Okay, the other ones have a trigonal prismatic coordination. So if you look at the coordination, it's explained on the basis of the crystal field stabilization energy. And if you're looking at molybdenum 4+, then you have 2d electrons. It's a d2 configuration. So if I put it in an octahedral field, then you have the very famous T2G EG splitting, and you'll have only 2 electrons over here. Okay. If this 2 electron system gets distorted, if the octahedron gets distorted somehow, then you see that the 2 electrons get more stabilized, okay, into just one of these orbits. And if you distort them further and put this orange atom on top of this one, so rotate it and make it trigonal prismatic, then your 2 electrons get stabilized in the dz square orbital, which is a much more stabler system compared to the octahedral polytype. Okay, octahedral coordination, the 1T polytype. So, but then 1T exists, and 1T exists when you exfoliate molybdenum sulphide using lithium. What does lithium do? Lithium puts 1 electron. Well, it's an electropositive metal, so it just gives off the 1 electron and becomes lithium plus. And where does this 1 electron go? This 1 electron goes and sits over here. And when that thing happens, then the T2G is filled, right? And it's more stable than the distorted form. So the distortion does not occur. Okay. And because of that, the 1T polytype gets stabilized. So you need some sort of chemical doping in order to stabilize the 1T polytype. And these studies are well documented. All right. To tell you something more about the optical well, of course, I'm telling you only about molybdenum sulphide, but any other semiconducting transition metal dichalcogenide also shows similar behaviors. Of course, the values would be different, but then qualitatively, everything is going to be similar. For example, you'll see these 2 excitonic absorption peaks, which are termed as A1 and B1. Okay, so you'll see these 2, 1.9 and 2.1 electron volts. You'll see these 2. And these will shift also. Okay, so this is for one monolayer, but these will shift also. Raman scattering. So these are things which you can use to identify what material you're forming. Okay. There's something very important over here, which is the carrier transport, because you want to use these nanosheets for a variety of applications. You want the charge carriers to move about, so one must study these mobilities, which are pretty decent at room temperature. But these mobilities are in the layer. Okay, when you talk of interlayer mobilities, they are very weak. I mean, one has to then do a tunneling kind, yeah. So from one monolayer to the next, and therefore within the layers, these are very high. And of course, you can even dope, for example, with rubidium molybdenum sulphide. It has a superconducting behavior too. Okay. So a lot of possibilities are there, and one needs to study quite a few of them. And the good part is that these are very, very stable. Okay, very chemically inert because it's a closed shell structure of the monolayer. So not many things can disturb it. Of course, you take it to very high temperatures, or you use very strong oxidizing agents. then yes, they do react with oxygen also. Okay. All right. So coming to the structure and properties of 2D materials, to sum them up, you see they have all these layered structure, okay, with molybdenum in the center, and now this is a trigonal prismatic coordination. Okay, this is the most common one found in nature, not the octahedral one, which needs to be stabilized. So yeah, these are your layers, okay, separated by about 3 angstroms or so, van der Waals separation. And you have a lot of properties. One is the tunable energy band gap. I'll discuss that in slightly more detail by showing you some examples. And there's an indirect to direct band gap crossover, excitons, which are very, very strongly bound, and that's why you can observe them. Mobility is very high. Again, we'll see some examples where we can use these to our advantage. And we have a high specific surface area, and therefore associated with it a very high catalytic activity, or the catalysis happens to be on the surface. So one could separate these two different kinds of applications, as has been done in the literature, although I wouldn't call them the basal plane applications, as people say. Well, they are from the electronic structure of the material. So you have a lot of optoelectronic device applications, spintronics, capacitors, batteries, or you have these edge site applications, which are more catalytic in nature. Okay, so we'll show some of this. We'll discuss some of these applications when I show you some bit of the research. And we have a lot of synthetic routes of two-dimensional transition metal dichalcogenides. Exfoliation being the most easiest common route that has been exploited. Mechanical, so you can do sonication. Liquid exfoliation, where you can actually use chemicals also. So more of chemical exfoliation, I would say. Then these more expensive methods, which give you very good quality materials, but in very, very low amount. And then the cheaper ones of solvothermal synthesis or colloidal synthesis, which also give you some very interesting materials, but much easier to follow, either exfoliation or chemical methods. CVDs and MBs cost too much. So briefly telling you, we are colloidal chemists, and we adopt our synthesis methodologies from what we've learned for the past so many years from colloidal chemistry. And briefly telling you about the synthetic methodology is this thing on the left. So we take a round bottom flask, put it in a heater, okay, heating mantle, on top of a magnetic stirrer, and there's a temperature control, which is very essential. And then you could, for some reactions, use a Schlenk line, which means you do this under inert conditions, and the chalcogenides definitely require that to make, it's for the precursors. MOSC2 otherwise is stable, MOS2 is stable. Then there's a septum for injecting things, or even taking out things when you want to monitor them. The temperature controller is a good precise PID1, and not very expensive. You can get it in the local markets. Now, what you take is a salt. Well, since this is adopted from the synthesis of cadmium selenide, so you take cadmium salt over here, okay, and take a high boiling solvent, for example, octadecene or trioctyl phosphine oxide, lots and lots of them. And then you heat them to a very high temperature of about 300 degrees C. Okay. At that temperature, you inject the selenium precursor, for example, trioctyl phosphine selenide. All you have to do is take some selenium powder and mix it in trioctyl phosphine, and this will form. Okay. Now, once you've injected this, cadmium and selenide start to react, and there's a sudden burst. I mean, at 300 degrees, it's going to be very fast. So all cadmium, all selenium available, they start to find each other and form these small particles, which are called nuclei. Okay. And when these nuclei get formed, and since I'm injecting something at a lower temperature, these are room temperature trioctyl phosphine selenium, which I inject, the temperature falls suddenly. Okay, from 300 it will fall down to about 240 degrees. So at that temperature of 240 degrees, what is ensured is that no more precursors break, okay, and form nuclei. But what does happen is all the precursors get deposited on top of the nuclei and react at the nuclei surface. So what you're doing essentially is something known as separation of nucleation and growth. And this has been known since 1950 by the models of Lamer and Dinager, who said that if you can separate nucleation and growth, then you can get very, very monodispersed colloids. Okay. And which is naturally because, you know, you have nucleation at the time of growth, then you'll have smaller particles and larger particles all forming together. Okay. So that's very important, and that is taken care of by these high temperature injection routes. Okay. And then you have, of course, there are other ways, water soluble particles. If you want to make, you could make it straight away by just using a KIPS apparatus for H2S, you know, into cadmium salt, and then or H2SE or H2TE. This is something which we've done in our college practicals, school practicals, where we had to determine cadmium as a cation. Okay, so something similar, but always in the presence of some capping agents. You see, even SR something is shown over there. So these are all capping agents, the gray ones, which stabilize the particles and also make them soluble. Okay, so all our nanomaterials that we make using the colloidal techniques will always have some capping agents. For example, trioctyl phosphine that is used as a solvent, or trioctyl phosphine oxide. So both of these are also capping agents, which means they surround the particle, and because they have these long organic chains, they also make the particles soluble in organic solvents, non-polar organic solvents, like toluene, hexane, and so on and so forth. If you wanted to make water-soluble particles, you could use capping agents that have a lot of OH or COH or NH2 groups. If you want, you can also change the ligands by doing something known as ligand exchange. So you can make something water-soluble from oil-soluble, you can make it into water-soluble. Okay. All right. Now, once you've synthesized these particles, you'd like to characterize them. And again, from examples of the colloidal synthesis of cadmium selenide, this is a typical transmission electron micrograph for these particles. And you see these are monodispersed in size. Well, and you can do high resolution transmission electron micrographs, see the lattice plane spacings, and you see this one is 0.357, this is 0.350, and 0.217 and 0.219, and that difference tells you that this fellow happens to be a woodsite crystal lattice, and this fellow happens to be a zinc blend. And when you look at the diffraction patterns, you see 111220331, and here you see 002. Okay, again 002 is typical of woodsite. But when you have very small particles and you record a diffraction pattern, you do not see very sharp peaks. What you see is very broad ones, okay? And you can hardly differentiate between zinc blende and woodside. All this, there's this slight thing which will tell you that this is woodside because you have some intensity for the 103 peak, whereas you have a dip over here at that position. But you know, when they are very small, they are polymorphs and they are all related by 60 degrees rotation. So zinc blende and woodside, they are both related, right? Both tetrahedral coordination. So one can even change into the other one if you have enough temperature or if you have enough energy. Also, you need to characterize these particles by means of spectroscopy, absorption spectroscopy, UV vis absorption particularly. And you can see all the excitonic features, the first, the second, third, and people have even observed up to 7 excitons. Okay, so these are all visible. I mean, but we'll have to go to higher energies, lower wavelengths, of course. And then the good thing about some of them is they are also fluorescent. So they give you emission. And these emissions are what I showed you. For example, this one is roughly about 575, so it would be yellowish in color, greenish yellowish, more towards yellow. So you could, you know, crystallize in different crystal structures. You can have, and you can control these. I'll discuss a bit more about that. How you can control this is something very easily understood by the particle in a one-dimensional box model. And the most important equation that you need to remember about the particle in one-dimensional box is this particular equation. E is equal to n square h square by 8 n a square, where a happens to be the length of a box in one dimension. Okay. Also, if you take it to 3 dimensions and make it a spherical box, then a happens to be the radius. Okay. Of course, you need to solve these equations, but anyway, that's the end result. This is quantum confinement, right? If you have a small value of a small radius of the particle, then you have a large value of E. Okay, and the energy is of a particle that is inside this box. So treat the nanoparticle as the box and treat your charge carriers as particles. And we are talking of semiconductors, so you don't have any free charge carriers. The free charge carriers arise when you excite these materials. So think of the band gap, and then you have an excitation across the band gap. You have an electron over here, and a hole remains over here. So both the electron and hole, they are excited. Okay, and because they're excited, you have their energy levels, and those are the quantized energy levels. And they depend, the energies depend on the size of the particle. Also, well, actually, I should show you over here the same equation written for electron and written for the hole. And these are your quantization energies for the electron and the hole. Okay, this is the Coulomb attraction term between the electron and the hole in a particle of radius r. Okay, because they are negatively and positively charged. And of course, if you want to be more precise, you can add on the polarization term, which the electron and hole polarize the lattice, and many more perturbative terms. And this is the bulk band gap. Okay, so the bulk band gap increases because of quantization and is stabilized a bit because of the Coulomb attractive term. But in general, it increases and this is called the effective mass approximation, or it was first given by Louis Bruce, so it's also known as the Bruce equation. The band gap, if you see for the bulk material, is small, And as you reduce the size of the particle, it keeps on increasing. And this is exactly the picture that I was showing you earlier. These are small size particles. Okay, so they are excited by the energy and then they emit. So these are all fluorescence images. So they emit at a larger energy, or in the blue. And the small size particles emit at a smaller energy. Okay, that is red. So you can essentially tune the energy by changing the size of these particles. Okay, and we've done a lot of work on this. We still continue to work on this, but today I'm going to tell you more on the 2D transition metal dichalcogenides. Anyway, the principles are the same. Okay. And I would then distinguish between materials which are confined in all three dimensions vis-a-vis nanoplatelets or 2D materials. So we do have the same things with the 2,6 semiconductors, and although you have these quantum confinement effects in both the cases, you'll see when you grow these, and if you grow them for a longer time, this absorption peak shifts to the red. And this is the fluorescence, which also shifts from green towards red. Well, the colors used are typically the colors that we see for these nanoparticles. Okay, so you can actually tune the size by changing the reaction time. Okay, and likewise, you can tune the thickness of the nanoplatelets by changing the reaction time and concentration and everything. But if you look at the fluorescence over here, okay, this is roughly about 10 nanometers or even less than 10 nanometers full width at half maximum, where here you'll get close to about 25 to 30 nanometers. So this precise definition of the thickness, it's either 3, 4, 5 monolayers, and that is the one that is the confined direction. Otherwise, it is very large in the lateral directions. So you will get very, very sharp emission features, which means even better colors, color purities that you'll get when you have two-dimensional materials. All right. So that's pretty much about some of the basics that I told you, and we are armed with a lot of knowledge, and we should look at some of the research that has been carried out in transition metal dichalcogenides, and particularly started by Razi Ahmed, who worked on molybdenum sulphide, and did Sushma, who did a lot of work on the time-resolved aspects of these materials, and then Shamim, whose work I'm going to present today, who worked on molybdenum selenides mainly, and Sushnata, she did a lot of photoconductivity measurements. So I must acknowledge all these colleagues, collaborators, students of, so they're essentially students and postdocs over here, who worked on these materials. Okay. So coming to molybdenum selenide, the way we make these molybdenum selenide is by using heptamolybdate and making the acetyl acetonate of this one. Okay, nowadays you can get these materials off the shelf as well, but when we started with heptamolybdates. And then putting some selenium precursor, you could use trioctyl phosphine selenium, or we use something like olyl amine selenium. So olyl amine is the capping agent in this case. And then you get molybdenum selenide nanosheets. Okay. But if you look at the other approaches, mostly CVD, MBE, exfoliation, then what you'll get is very flat triangle or hexagon looking sheets. But when you look at our approaches, you get these crumpled structures as shown in the TEM. And that is because the colloidal approaches give you ample room for having defects. And these defects are nothing but absence of selenium atoms. Okay, when you have these absence of selenium atoms, the molybdenum atoms tend to get attracted to the next nearest neighbor selenium atoms, and therefore the sheets fold or get crumpled like this. Okay, and you can see these crumples very easily in the TEM images. All right. But the good thing is, well, initially you might think it's a bad thing to have defects, but it's actually a good thing, and I'll tell you soon. Okay, so how do you characterize these sheets? Again, go back to some of the basic characterization tools. Diffraction, I'll show you more later. But diffraction, when you have 6 monolayers, well, for diffraction, you cannot have diffraction with 1 monolayer. In fact, you need a few monolayers to have a decent intensity. So when you have 6 monolayers, you look at the 002 peak, and 002 is this direction. All right. And as I said, if you have 1 monolayer, you have only 1 monolayer. You do not have any monolayers in this direction, so you should not get the 002 peak. With 6 monolayers also, it's difficult because of the intensity is low, and so 20 scans added average give you some intensity. Sorry, is there any question somebody wants to ask me? Yes, Abhisri? Do you have a question? Yes, please, Jignesh. You'll need to unmute yourself, and Abhisri, you'll
Hello,
need to
sir.
mute yourself, I guess, because there's some noise coming. Yeah, Jignesh, please
Hello,
tell me.
sir. Sir, is there any technique by which 1T, 2H or 3R can be determined when it will be produced?
See, of course, the diffraction tells you about it. X-ray diffraction, you'll see different sets of peaks over there.
All right, sir. Thank you.
Also remember, 1T is metallic.
All right, sir.
All right. Yeah, so when you have these 6 monolayers, then you tend to see some diffraction peak appearing. But with 1 monolayer, even after adding 20 scans, you see absolutely no diffraction peak. So it's not a confirmation, but I can say that yes, there are hardly very few monolayers over here. There's some more. Okay. You could use the Scherer equation to determine the thickness over here, by the way. Okay. And how do you make these 1 monolayer 6, or for that matter, control these monolayers, is simply by changing the concentration of your capping ligand. You see, if you have a lot of capping ligand, all this ligand will come on top and it will suppress the growth along the 002 plane. Whereas if you have low amount, then this growth is allowed. So by controlling this, you can control the number of monolayers. Okay. 1, yes, you can get very easily. For greater monolayers, you'll have some distribution of sizes. And as you've seen the particle in a box, the effective mass approximation, these excitonic, the A and B peaks for 6 monolayers are at a lower energy, but for 1 monolayer, they're at a higher energy. This is wavelength scale, sorry, the lambda is missing in nanometers. So this is at a higher energy, and that is simply the quantum confinement effect that comes into play.
Thank you, sir.
Yeah. So looking at some of these applications, when you have so much of defects, we think of the electrocatalytic HER reaction, the hydrogen evolution. Okay. And so I'm sure some of you might be new to this, so let me tell you how exactly it's done. You take a take an electrode. Okay, so take any electrode. We prefer the glassy carbon electrode, but that's not a limitation. You could use it. You put your material on top of the glassy carbon electrode, and then you take another electrode, which is a standard platinum electrode, and then you start applying a voltage. So after a certain voltage is applied, these materials would pass on the electron to H2O, and which is of course H plus and OH minus. So H plus takes up the electron and becomes H2 gas. Later on I'll show you the mechanism also. So H2 gas gets evolved, but the electron is taken up, and therefore the circuit is completed now. Okay, and because the circuit is completed, the electron moves on to platinum. So you will see a current flowing. Okay, and this is what is shown over here. Initially, for certain voltage, you do not see any current, and then you see that some current starts flowing. So typically, the reported values are at minus 10 milliamperes per centimeter square of the material, is what you report, okay, as the onset voltage. All right, and for platinum, ideally it should be 0, but then everything is not ideal, and then you have a lot of things happening. Kinetic factors to come in. Yeah, platinum, it should be 0 because that is the normal hydrogen electrode, and it should evolve hydrogen without any efforts. So instead of glassy carbon, when I put platinum over here, I get an onset voltage of about 100 millielectron volts. Okay, and when I put molybdenum selenide 1 monolayer, what we get is 210 millielectron volts. For 6 monolayers, what we have is 220 millielectron volts. And when you have bulk molybdenum selenide, then that onset potential is about 500 millivolts. Sorry, why I'm saying electron volts, millivolts. All these. Okay, and then what also matters is the kinetics. So how fast, how steep this slope is, which essentially tells you that what you have is that, even for a very small change in voltage, you can get more currents or produce more hydrogen. That is called the Taffle slope, and that is shown over here. Well, the inverse of this slope is actually called the Taffle slope. So the lower the value of this slope, the more hydrogen you can produce. And you see that 38 for platinum, 54 for MoSe2 1 monolayer, 68 for 2, 110 for the bulk MoSe2. So you're getting a pretty decent value with MoSe2 compared to platinum. And platinum is roughly about 60-70 times more expensive. Okay, the reason you're getting slightly more value is shown over here, because with MoSe2, you go from 1 monolayer to 6 monolayers to bulk, the impedance increases, so the resistivity essentially increases. Okay, otherwise the currents that you get out of this are quite stable over time. And of course, when you have 1 monolayer, it has to travel in this monolayer and then goes on to the electrode. When you have multi layers, then the electrons have to jump or tunnel across this. So that's why you get much higher. And when you have bulk, you have even more monolayers, so the tunneling is much more. So that is very, very well understandable. Now, what else can you do when you have so much defects? And already you see that you can use molybdenum selenide in place of platinum. So we also make dye-sensitized solar cells. and there also we use platinum. So can we use molybdenum selenide in place of platinum in the dye-sensitized solar cells? So let me just show you what solar cells are all about. And to start with, this is the spectrum, the solar radiation spectrum. 3% in the UV, 44% in the visible, and 53%, quite a huge chunk in the infrared region. Now, of course, this yellow one is at the top of our atmosphere, and the red one is what we receive at the Earth's surface. So one has to worry about these things and see that a material could absorb this sunlight, right? And the kind of materials that have been studied ever since are all shown on these NREL charts and updated very, very regularly. Okay. So if you look at this, this is a very busy chart, by the way. So let's look at silicon. Silicon has been there since 1975-76 and gone from a very small efficiency of 10-12% all the way to now 23%, 24% are regularly available in the market. Okay, but of course there are these there's single crystal silicon and amorphous silicon, but you also have a lot of heterojunction cells, which I'm not talking of. They're used for more niche applications like space and all. Very, very costly indeed. But this is what you get in the market. Then, of course, there's the dye-sensitized solar cell, which started in 91 by the efforts of somebody called Michael Grätzel, and that's why they are also known as Grätzel solar cells, or Grätzel cells. And they started with a small efficiency of 4% around, and now I think about 14-15% is what is possible. Okay. But if you look at another material, instead of dyes, if you use quantum dots, then the progress of quantum dots has been much steeper. Okay. And they're also at about 15%, but much steeper progress. And steeper progress is something more promising, I guess. The steepest one happens to be the perovskite solar cell. Not just steep, but the absolute value is also very high. As I said, 24-25% is possible now, but one has to look for the stability of these perovskite materials. All right, so a dye-sensitized solar cell and a quantum dot sensitized solar cell. In fact, perovskites were also made in the same configuration to start with. The principle of these solar cells is fairly easy to understand. If you look at this N719, it's a ruthenium dye. Don't worry, it's some structure. Ruthenium with a lot of rings, organometallic kind of structure. So this dye has a homo-lumo gap over here. And when you shine light, so it's in the infrared, its absorption is at 719. When you shine light, then the electrons go over there. Okay, and these electrons are then channeled over to titania, which are then thrown over to the fluorine doped tin oxide. So this is what it looks like. This is FTO, or the transparent conducting oxide, fluorine tin oxide. So this is one plate. There's it's normally FTO coated on glass. Okay, then you put TiO2 nanoparticles, mesoporous nanoparticles, roughly about 20 nanometers on top of this, make a paste and put it, and then dip it in the dye. So the dye gets absorbed, and from white color, it just changes to dark brown, black kind of thing. Okay. Now, on the other hand, you also want to get the holes out of the dye. Okay, so that again, it becomes neutral. Or, you know, getting holes out is actually pushing electrons in that way. Anyway, easier to think of holes in a bucket of water. Yeah, easier to think of bubbles. The same analogy goes over there. So the holes, they have to go and reach the counter electrode. And the holes have to go from here and reach this counter electrode. Okay, and then the circuit is complete and you make an external circuit. And for that, you need a redox couple over here. The electrolyte, iodide, triiodide, which can be oxidized and reduced. And who does that? The platinum counter electrode catalyzes the reaction. Okay, so then the holes can be transported across. And as we've seen that molybdenum selenide could replace platinum with a very, well, that's a very good efficiency that I showed you for the hydrogen evolution reaction. It could perhaps also catalyze the iodide-triiodide couple, and for that you need to do a very simple experiment called a cyclic voltammetry. And I'll not explain much over there, but what you see, these oxidation peaks and reduction peaks, they can be achieved. So this is the cyclic voltammogram for iodide-triiodide couple, and the same oxidation reduction can be achieved by MoSe2 that was possible with platinum. Okay. The only thing is that MoSe2 is slightly more resistive compared to platinum, and that is shown in the efficiency of the solar cell that we finally fabricate of the device. Platinum is about 8% and molybdenum selenide is about 7%. I think the best device is 7.2%. Okay, there's a question, but I told you it's difficult for me to read. Lifetime of what? Elil Arasi. Lifetime of DSSC meaning the stability, or what kind of lifetime are you asking? Okay. If you're asking for the stability, yes. Okay. Then those are things that, we've not optimized devices. We just, if you look at this stability, we've just done it for 5 days. Okay. Yeah. So we've not studied really much stability issues over here. But MoSe2 is pretty stable, so I'm sure it should be almost as stable as platinum. Well, as long as you're working in decent voltage ranges. Yeah, the moment you take it to a higher voltage, then selenium can get oxidized on the surface. Yeah, so you have slightly lower, but then you're reducing the cost 60-70 fold. It's much better. I have no idea how to improve the stability of DSSCs. I just use them as a proof of principle for my materials, but I'm not somebody who works on solar cells, and that question somebody who really works on solar cell research would be able to answer. Okay, Rakesh? Okay, thanks. All right. So, you can have only so far applications with just MoSe2. But the real fun comes when you start making heterostructures of these materials. Okay. And when you want to make heterostructures, then you're looking for two materials which have low lattice mismatch. So Shamim selected molybdenum selenide and cuprous sulphide. Okay, they both have hexagonal structure. Okay, we know MoSe2 2H phase band gap. Okay, the most important thing to look is A and B in the hexagonal. C is perpendicular, okay, to the growth direction, so I don't need to worry about C. But A and B is 3.29 angstroms. Here it's 3.79 angstrom. roughly about 7-8% lattice mismatch. Okay. The good thing is that this is a semiconductor. This Cu2s could be metallic. Zero band gap. So, how to make these heterostructures is again something which Shamim thought of. You take these defect-rich MoSe2, as I told you how to make them. Put some dodecane thiol on top of it. Now, remember these defects were because of absence of selenium, or these were selenium vacancies. So the moment you put thiol, which is sulfur-rich, it goes and sticks on top of this. Okay, so these dodecane thiol chains stick on top of this. Okay, and then you add cuprous iodide. Now copper is also very fond of sulfur or chalcogens, so cuprous sulfide ions get formed on top of these defects. Okay. Something very interesting over here, another characterization technique, Raman spectroscopy. Well, now if you look at these two peaks, these are the EG and the A1G peak, E2G and the A1G peak. And so E2G happens to be the two-dimensional Raman frequent peak, which is associated with in-plane vibrations, and the A1G happens to be a one-dimensional, which is associated with out-of-plane vibrations. But this fellow is not there in bulk MoSe2. Okay, this is because of the defects that we have. You'll never see this peak in a CVD grown sample. The moment we put DDT on top of this, these defects intensity goes down, and you expect that to happen. So you could actually study how much defects are there in your sample by, or whether your defects have been passivated by looking at this defect-related Raman peak. Of course, I told you there are other characterization methods. XRD, I've already told you. This is AFM. Okay, so AFM shows you that this is 7 angstroms, exactly. No, sorry, 9 angstroms, exactly 1 monolayer thick. Okay, but when you make these heterostructures, these are your molybdenum selenide sheets. These are separately formed cuprous sulfide. So when you don't have molybdenum selenide, this is what it looks like. But when you form it on top of MoSe2, then these are your heterostructures. Okay, these crumpled sheets, and on top you can see all your Cu2s particles. You can also do some high resolution imaging and see all these lattice fringes and match them back with the diffraction peaks. Some more things over here. You see all these heterostructures. You can do an elemental mapping, and all these things are now possible because we have the central research facilities. Well, not just IIT Delhi, but you could even use some other central research facilities. But the idea is that you don't have to maintain an equipment at home. Okay, in your lab, that's very expensive, right? Just pay some small amount of money and get all these things done, and know that molybdenum, selenium, copper, sulfide, everything is there. Okay. But in what state? For that, you again go to the central research facilities and do photo emission experiment. And you'd understand what the structure of these materials is exactly. And if you see molybdenum, you'll get 2 different signals over there. Well, ignore that, that's because of sulfur. But you get these 2 different, the green and blue. One is ascribed to selenium bonded, one is ascribed to sulfur bonded. Selenium, you get only one feature, the blue one. Okay. Which means selenium is bonded only to molybdenum. Copper, again, only one feature, which means copper, cuprous sulfide is what we were making. So copper is bonded only to sulfur. Sulfur, again, you get two features. One bonded to molybdenum because of the DDT, and that's why that binding energy is slightly higher over here, and another bonded to copper. Some of this sulfur also gets oxidized because it's on the surface. Okay. So now you understand the structure of these materials, and these are these heterostructures. But what is the electronic structure? This is something where my colleague from the physics department, Shashwata, steps in, and he does all the theoretical calculations for us. And Shashwata, so this is just the summary of the theoretical calculation, which I show over here. This is the density of states. Okay. And if you look at this density of states, the total one is in blue and red for MOIC2 and green for cuprous sulfide. Well, let me show the schematic over here, which is more easy to see. What you see is that the valence band of cuprous sulfide lies above the valence band of molybdenum selenide. Okay. And that is, the cuprous sulfide states are on the top of the valence band, whereas molybdenum selenide states are not. And the conduction band of molybdenum selenide, well, it's identical to the blue curve here. So the red and the blue are identical. Okay, lies below the conduction band of cuprous sulfide, which is over here. Okay, so he makes all these heterostructures, makes a model of these heterostructures and calculates it. All right. So what it tells me is I'm forming some sort of a PN junction or a type 2 semiconductor heterostructure. Okay. So the electrons would go to molybdenum selenide because that's a lower energy for them. The holes would move towards cuprous sulfide, which means I have a natural extraction of electrons and holes, right? If I have that, then I'm at an advantage already for solar cells, photovoltaic devices, or photoconductivity devices. So let's try to make a photodetector, which is very easy to make. All you need to do is take some p-type silicon, put n-type MOSE2 so that this acts as a barrier layer. It doesn't allow the electrons to move here. Then you take molybdenum selenide cuprous sulfide, your own material, put it on top, and then on the top of it put some gold contact electrodes. Now you shine light and give it a voltage and see what happens in the absence or presence of light. And what you see, if you have just molybdenum selenide, the red curves, then there's hardly any photocurrent that comes out. But when you have MOSE2 CO2s, then you have an increase of about 4,000 folds in the photocurrent. And the good thing is with MOSE2 CO2s, it's not actually CO2s. Okay. It is actually CO2 minus S X sulfide. Okay. It's actually 1.97 is what we've determined. And because of that, because of these copper vacancies, the holes that get created in the material, and these holes show as plasmon resonances in the near infrared field. And these plasmon resonances also help in a photoresponsivity in the near infrared field. And this infrared photoresponse behavior has been very useful for satellite applications. And ISRO definitely demands a lot of material from us. Okay. These are very, very stable devices in time. Okay. Again, I'm not very particularly keen on doing a lot of stability tests, but for the papers you have to do it. And then I have some collaborators over here, Shubhendu at SSPL and Professor S.K. Ray in Kharagpur, who help do all these measurements for us. Oops, why did it run away? Something's happening. Okay, go slow. All right. So anyway, we can get a lot of enhancement over here. when you illuminate with that. So good photoconductivity behavior. Again, since we have these MoSe2 on Cu2s, and Cu2s has been used as the counter electrode for quantum dot sensitized solar cells. This one having, everything on the monolayer would give me much better charge carrier mobility. So, well, these are cadmium selenides, so they are not very efficient, but then it does increase, right? The performance does become better. This is just the photovoltage with the current density. So from 3 to 3.6. Anyway, the numbers are not very impressive, but it's better. What else can we do? Again, we can go for the HER and OER, but again, look at the theoretical calculations over here, put them on energy scale properly, and bring in your normal hydrogen electrode. Okay, so this energy scale is with respect to vacuum, but this is your 4.44 minus 4.44 is the normal hydrogen electrode. And now you slightly increase the voltage, okay? And what you do, you take your working electrode, which is my glassy carbon, you'll take it down, and the holes that were there on cuprous sulfide can then flow over here. Likewise, you could take the glassy carbon electrode slightly up, and the electrons would then go from the glassy carbon to molybdenum selenide. So this is good for oxygen evolution, where the holes can be taken up, or this is good for hydrogen evolution, where you can give the electrons to the material. So H plus takes up the electrons and becomes H2. Okay. So this is the entire mechanism written over here. Maybe if somebody later has a question, we can discuss. Otherwise, I'll just skip it. I think I'm nearing my end time. So once you've done all this, then you measure, right? And the mechanism is important actually, because you need to do the measurement under alkaline conditions. Okay, and if you want to do your OER under alkaline conditions, you cannot do HER under acidic conditions, which was normally the case, the example that I showed you earlier. But then you have to worry about alkaline conditions. So the mechanism is slightly different from what you have under acidic conditions. And you can well understand that if you had H plus, it was easy to reduce it, but now you're doing it under alkaline conditions, so it will get slightly difficult. But first, let's take a look at the oxygen evolution reaction. And this particular graph is for iridium oxide. Okay, the color tells you what the graph is for, iridium oxide. That is the standard. Okay. And when you have iridium oxide, this is what you get for oxygen evolution. Roughly 1.4 volts versus the hydrogen electrode. And then, but with molybdenum selenide cuprous sulfide, the blue curve, it starts at a slightly higher voltage, but then rises much faster. Okay. Right. And there all these comparison with just MoSe2 and just Cu2s and just glassy carbon, just to show that these are not artifacts, but these are real values. And again, Taffle slopes and the conductivity arguments all coming in, stability issues. So everything falls in line. It's a very, very good OER active material. But then the thing is that it's not, is it stable? Okay. And it's not stable. What happens? The copper from +1 gets oxidized to copper 2+. Okay. And then the good thing is that this catalytic activity continues for hours. Well, we've recorded for 8 hours, and later on we recorded for 48 hours. It continues. And another good thing is that the structure of the material does not change. So whatever is happening on absolutely on the surface, since XPS is very surface sensitive. Whereas XRD pattern just shows me that, okay, before catalysis, after catalysis, it's all the same. And based on this, we arrive at a mechanism over here that we have both copper 2 and copper 1 centers that are present because copper gets oxidized. Okay, so copper 1 is free for the OH minus to attack, and then you have both of them as copper 2 for some time. Okay, and then another OH molecule ion attacks over here. Okay, and you know, it takes off an H2O, another OH attacks, the peroxo forms, and this peroxo then allows the O2 to come out. Okay, that's my oxygen evolution step. And when this O2 comes out, the copper 2 goes back to copper 1. Okay, so it's dynamic between copper 2 and copper 1, and therefore, you know, even this is a catalytic site because it's already OH minus. So if this releases, then copper 1 will come over here. And well, although a mechanism is of course hypothesis, but it is supported by our data that comes over here. Also, the fact that if we use this mechanism, the energy calculations show that the green one for MoSC2CO2S happens to be the lowest energy path. Okay, this is again Shashwata's calculations that come in over here. Also, it's possible to do hydrogen evolution, so complete water splitting is possible. I've already shown you hydrogen evolution for alkaline conditions, and that was roughly about 200 millielectron volts, slightly less in case of MoSC2CO2S. But in case of alkaline conditions, it comes to about 400 millielectron volts, but it's still possible. Okay, so less efficient, but still it does happen. Again, energy calculations, everything, and Taffle slopes, they show that this is favorable to have the heterostructure for your fluids. All right, so Shashwata is very, very ambitious. He can do theory with everything. And since we are also working on perovskite materials, he went ahead and did theoretical calculations with cesium lead bromide on top of MoSC2, and said that, look, this is also a type 2 kind of a heterostructure. But now, with copper sulfide, I told you it's hexagonal and hexagonal, but cesium lead bromide is cubic structure. Okay, and there's no lattice match at all. How do I grow this? Okay, Shamim came up with a very bright idea, and what Shamim said was, okay, we have all these defects which are hungry for thiols, and then cesium lead bromide is always capped by amines. So let's take a molecule that has both thiols and amines. Thiols will go and stick over here, amines will be free. Okay, so this is 4-aminothiophene, one such molecule. There are many more that we've used. And he throws in then some cesium lead bromide on top of it. Okay, they go and attach over here. These are cesium lead bromide, that's the MoSC2, and when they are attached, this is what it looks like. A lot of washings have been done. Okay, again, all this familiar characterization techniques, I'll just skip this part. Also, the fact that they are stuck together is evident by monitoring the fluorescence spectrum of cesium lead bromide. So it has a fluorescence peak of about 515 nanometers. And when you bind them together using 4-ATP, it comes down completely. There's a huge quenching. But when you do not bind them and put a mixture of cesium lead bromide and MoSC2, then it doesn't come down so strongly. Okay, so there is some interaction, but when it's bound, the interaction is much, much stronger. Okay, also the same thing is evident from the time result photoluminescence studies. You know, when you have a quenching of any emission, then the lifetime of that species also goes down. Okay, I won't have time to describe that in great details, but Again, the photoconductivity measurements need to be done over here. And you see, this is for MoSe2 Cu2s. This is for MoSe2 cesium lead bromide, and it's a very flat photoconductivity device. You can, which means you can do a measurement at very low voltages also. Here, it's a sloping one. Well, although the values are more or less similar, but the dark values are much lower for MoSe2 cesium lead bromide, and the enhancement is roughly about 20,000 folds compared to 4,000 fold in MoSe2 Cu2s. Okay, so they are very good photo detectors. Well, of course, cesium lead bromide doesn't give you any photo detection in the infrared range. The geometry is exactly the same which we had earlier. Okay, so we can make all these devices, we can do all these catalytic activities. Essentially, I'll summarize my talk now. That energy happens to be the most worrisome thing for me, for most of the material chemists, for most of the material scientists. Yeah. And nanomaterials, and in particular 2D nanomaterials, are very promising for all these applications because 2D nanomaterials are flat and therefore you can orient them very nicely. You can also orient 1D, but 2D you can orient even more. I've shown you some applications of solar cells, photoconductivity devices, catalysis, and the take-home message is that heterostructures offer very good solutions for energy. Okay, we've worked on a lot of these heterostructures, in particular 2,6 TMDs. We've not worked on 3,5s, but then there are heterostructures. We're working a lot on ternaries and quaternaries, and they give even more new phenomena that one could not expect. The good thing is we can now make heterostructures even when the crystal structures are completely different. In fact, Ajit, the other student of mine, has also made some van der Waals heterostructures. These are very interesting ones. We're soon about to publish those results. What we lack is, of course, this thing. We need to study the excited states, and we are getting some instruments in the CRF. I hope another 1 year or so these should be active, because that is much required to understand all these properties and then get better device features. And without any doubt, I'll tell you that the road ahead is more 2D materials and heterostructure, and particularly trying to understand the interfaces. A lot is happening at the interfaces, and one needs to definitely understand those things. All right, I'll once again thank my entire group and all those members who've already left the group, and my collaborators and the funding agencies. And thank you all for your very kind attention and listening to me so patiently. If you have any further questions, I'll be happy to answer.
Thank you, Professor Sapra. It was very nice, and we learned a lot, specifically participants. So we have some time. So if there is any question, then participant may ask the questions, or they can put in the chat box also.
Okay, thank you. Thank you so much for patiently listening, Utpal, Yalil. Thanks, Dr. Swati. But you can speak. Or are they muted?
No. They can speak if
Okay.
they want.
Okay. Yeah. Thank you so much for your lovely compliments, Anandan, Pawan. I'll be more happy if you have more questions. But I have some questions for you. I have given it to Professor Hussain.
Yeah, I will place it to them at the later part of the program.
Yeah. So I hope you remember something from the talk.
I will share the recorded video also with them.
Okay.
So maybe if there is no more questions, we may conclude. And details about Professor is there in his website. So, okay, somebody is asking. So, sir, you can have a look.
Yes, yes, Dr. Swati, yes. So 1.97, 1.96, we've roughly about that is what we determined for our Cupra sulfide. Su chalcocite, yes. Yes, there are a few other phases now. When we got the XRD patterns, we did compare all of them, but don't ask me now. Great, you know much better. Okay, yeah, Chilrite and Covalite are also there, right? Good, thanks for refreshing my memory. Well, what can be used is a different question. Oh, great, so you work on thin films. Well, I'll have to, what can be used? One has to really see if it's forming this kind of a PN junction, the type 2 semiconductor heterostructure. If it forms, then one should try that. And if it forms, well, let me turn on my video so that I can show you this. Okay, so if it forms something, well, let's say this is my PN junction, okay? If it forms like this, where the levels are close, it's very good because you don't lose much energy. But if it forms something like this, somewhere halfway between, if it forms like this, it's more of a Z scheme. If it forms like this, then you lose a lot of energy. So one really has to look at what the energy levels of these different materials are. If you yes, from the XRD we got main phase was 1.97. How to improve the stability of DSSCs? Sorry, I don't work on that at all. I don't work on that. In fact, we make these just as proof of principle devices. You're welcome. Maybe I could borrow some thin films from you and try to make these heterostructures.
So, if there is no further questions, we may close the sessions. Thank you very much, sir, for giving the time with us and enlightening us with your activity and in this emerging area of research. So I am sure that the participants are benefited, and your details is there in the website. So participants, if you are interested, you can contact sir directly also.
Anytime.
And our main aim is this type of program is to have some kind of refreshment as well as collaborations or develop communication network also.
Great.
So you can always contact. Okay. So thank you very much, sir. And
thank you. It was very nice interacting with everybody.
Near future also we will have you with us.
Definitely, I love
some
to.
other programs. So thank you, sir.
Thank you so much. Okay, I'll take your leave.
Sure. And dear participants, so now this is time for lunch. So we shall again join here at 2:30. And Professor Tanushree from Bose Institute, she will be speaking on two-dimensional magnetism. So I request you all to join by 2:20. So I am closing it now.